ಅಲ್ಲ ಈಗ ಗೊತ್ತಾಗುತ್ತಲ್ವಾ ನಾನು ಮಾತಾಡಿದ್ರೆ? ಆನಂದ್ ಆನಂದ್
ಇಲ್ಲಿ ನಿಮ್ ವಾಯ್ಸ್ ಕರೆಕ್ಟ್ ಆಗಿ ಬರ್ಬೇಕು
ಸರ್. ಕೇಳಿಸ್ತಿದೆ ಸರ್, ಕೇಳಿಸ್ತಿದೆ.
ಆಡಿಯೋ ಕ್ಲಿಯರ್
ಏನ್ ಹೇಳ್ದೆ ಹೇಳಿ?
ಇಲ್ಲ ಏನು ಹೇಳಿಲ್ಲ ನೀವಿಂದ.
ಆನಂದ್ ಅಂತ
ಹೇಳಿ ಸರ್. ಒಂಚೂರು ನಿಮ್ಮ ವೆಬ್ ಕ್ಯಾಮ್ನ ಇದನ್ನ ಟಿಲ್ಟ್ ಮಾಡ್ಕೋತೀರಾ? ಮೇಲೆ ಒಂದು ಸ್ವಲ್ಪ ಕಟ್ ಆಗ್ತದೆ, ಮೇಲೆ ರಿವರ್ಸ್ ಡೈರೆಕ್ಷನ್. ಹಾಂ, ಇನ್ನೊಂಚೂರು ಕಡಿಮೆ, ಇನ್ನೊಂಚೂರು. ಹಾಂ.
ಓಕೆ. ಅಲ್ಲ, ಇದು ವಾಯ್ಸ್ ಕ್ಲಾರಿಟಿ ಇದೆಯಾ?
ವಾಯ್ಸ್ ತುಂಬ ಕ್ಲಾರಿಟಿ ಇದೆ, ಕ್ಲಿಯರ್ ಆಗಿದೆ.
ಇನ್ಫಾರ್ಮೇಶನ್ ಕ್ಲಾರಿಟಿ ಇದೆಯಾ?
ಅದು ನೋಡ್ಬೇಕು ಸರ್, ಅದಾದ್ಮೇಲೆ ಹೇಳ್ತೀನಿ.
ದಟ್ ಇಸ್ ಮೋರ್ ಇಂಪಾರ್ಟೆಂಟ್.
ಅದಾದ್ಮೇಲೆ ಹೇಳ್ತೀನಿ. ಅಸ್ಗರ್,
ಇಲ್ಲ ಅಂದ್ರೆ ಎಲ್ಲಿಂದ
ಅಸ್ಗರ್.
ಹಾಂ ಸರ್ ಹೇಳಿ.
ಒಂಚೂರು ಟಿಲ್ಟ್ ಮಾಡಿ ಅಸ್ಗರ್, ಒಂಚೂರು ನಿಮ್ಮ ಲ್ಯಾಪ್ಟಾಪ್ದು ಫೇಸು.
ಅಲ್ಲಲ್ಲ, ಅದು ನಿಂತ್ಕೊಂಡಾಗ ಇಲ್ಲಿ ಸರಿ ಹೋಗುತ್ತೆ ಸರ್. ಅದು ನಾನು ನಿನ್ನ ಕೆಳಗಡೆ ನಿಂತಿದ್ದೀನಿ, ಅದಕ್ಕೋಸ್ಕರ.
ಅದು ಓಕೆ, ಬಟ್ ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಅವಾಗ ಸರ್ ಕೂತಿದ್ರು, ಅದೊಂಚೂರು ಅಡ್ಜಸ್ಟ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡೋಣ. ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಡೌನ್ ಬರಬೇಕು.
ಡೈರೆಕ್ಟ್ ಏನು ಮಾತಾಡ್ತಾರೆ, ಜಸ್ಟ್ ವಾಯ್ಸ್ ಚೆಕ್.
ಹಾಂ, ಓಕೆ ಸರ್.
My voice, it will all be same, no? Hello?
ಕೇಳಿಸ್ತಿದೆ ಸರ್.
Fantastic. Okay.
Good morning, sir. Welcome to the. Yes, sir. Good morning. This one, sir. Iyer sir ಬಂದ್ರು. Join ಆಗ್ತಾರೆ.
Anand, can you hear me?
Yes, sir.
Okay.
Good morning, sir.
Morning. Yeah.
It's
So
very
right
clear, sir.
now,
Yes,
okay, very good. I'll just open the video. In the beginning, I'll open it. After that, I will.
Okay, sir. Sir, I will ask Madhusudan, sir. He has shared his PowerPoint. I
Yeah.
will ask him to stop that, and we can check for 2 minutes.
No, it's not required.
Okay.
At this particular point, let it be. Let's not
Okay,
change
sir.
anything. I'll
Okay.
just turn on the video so that
Okay.
you can see me.
Yes, sir. I can see you now.
Okay, good. So after some time, when Matsuna starts speaking, maybe I will just turn off the video.
That's it.
Is that okay, or what
Yes, sir.
what have you planned?
No, that's the same way, sir. I mean, first, sir will talk. Sir will give you. Madhusudan sir will give the talk.
Okay.
So, because we are only 3, I don't think. I mean, the video will create any problem with the bandwidth.
Yeah,
But
my,
even
my
then,
problem
it
is
is.
the bandwidth on my side,
Yes, sir.
my
Yes, sir.
connect. Yeah.
Yeah, yeah. That is.
Sometimes.
That's. It is better that we switch off our videos for the
Yeah,
first talk.
exactly.
Yes, sir.
How many people are in the auditorium currently?
I didn't go. I'm in my cabin. Maybe around 20. Hello,
Okay.
sir.
10.
10 idara, sir?
10.
10.
And how many on the the YouTube?
2 bears is not yet started, sir. It will
Okay.
get started in few minutes.
Okay.
ಅಲ್ಲೆಲ್ಲ ಬರ್ತಿರ್ತಾನೆ. ಅದಕ್ಕೆ ಎಲ್ಲ ಸ್ವಿಚ್ ಆಫ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡ್ತೀನಿ. ನಾನು ಇಲ್ಲಿ ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡ್ತೀನಿ, ಅವಾಗ ಕೆಲಸ.
ಗೊತ್ತಾಗ್ತಿಲ್ಲ ಯಾವ್ದಂತ.
Sir, once the program starts, hello.
Yes.
So, sir, can you hear me? Once the program starts, I will mute all the other participants except the speaker.
Very good. Thank you.
That should be good, because if there will be no disturbance for the speaker.
Anand sir, am I audible?
Yes sir. Yes sir.
Yeah. Okay. ನೀವು ಇಲ್ಲಿ ನಿಂತ್ಕೊಂಡು ಮಾತಾಡ್ತಿರಲ್ಲ.
ಇಷ್ಟೇನಾ? I don't have to do anything.
You don't have to do anything, and whatever you speak, it will be like.
Okay.
ಇಲ್ಲಿಗೆ ಆಡಿಯೋ ಕರೆಕ್ಟ್ ಆಗಿ ಬಂದ್ರೆ ಲೈವ್ ಸ್ಟ್ರೀಮ್ ಕರೆಕ್ಟ್ ಆಗಿರುತ್ತೆ.
No, they are on phone call.
No, they will have to stop now because everyone is in meeting. So if they cross talk, it will be going on to.
ಅಸ್ಗರ್ ಒಂದು ನಿಮಿಷ. ನಾನು ಪ್ರೋಗ್ರಾಮ್ ಸ್ಟಾರ್ಟ್ ಆದ್ಮೇಲೆ ಸರ್ದು ಟಾಕ್ ಶುರು ಆದಾಗ I will mute all the other members. Right? Only the other way that we can commute is either through the chat.
No. You should not mute Madhusudan sir, because Madhusudan sir is on live.
Bere ibbarna. Bere other participants, I will mute them.
Okay.
I will mute them so that it will not create a disturbance.
Okay. Right.
Okay. And the other mode of communication between us, if it is required, is through the chat. You can chat or you can call me on the phone.
Okay. Right, sir.
Anand.
Sir.
I am starting now.
Okay, sir.
Hello?
Yes, sir. Please, sir, you can.
Anand, I'll be starting now. So
Okay,
next,
sir.
keep yourself free, okay?
Okay, sir. I will.
ಇವಾಗ ಕಾಣಿಸ್ತಿದೆ ಅಲ್ವಾ ನಂದು ಸ್ಕ್ರೀನು?
Yes, sir.
Teams ಅಲ್ಲಿ?
Okay. Yes, sir. ಕಾಣಿಸ್ತಿದೆ. ಸರ್ ನೀವು ಒಂದ್ಸಲಿ ಫ್ರೇಮ್ ಟೆಸ್ಟ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡಿ ಸರ್. ನಿಂತ್ಕೊಳ್ಳಿ ನೀವು ಸ್ಟ್ರೈಟ್ ಆಗಿ ಇದ್ರ ಮುಂದೆ, ಲ್ಯಾಪ್ಟಾಪ್ ಮುಂದೆ. ನೀವು ಹೇಗೆ ಅಡ್ರೆಸ್ ಮಾಡ್ತಿರೋ ಹಾಗೆ. ಓಕೆ. ಇನ್ನೊಂದು ಚೂರು ಡೌನ್ ಮಾಡೋಕ್ಕಾಗತ್ತಾ ಲ್ಯಾಪ್ಟಾಪ್ ಇದನ್ನು? ಅಲ್ಲ, ಡೌನ್ ಅದರ್ ಸೈಡ್. ಹಾಂ, ಒಂದು ಸ್ವಲ್ಪ ಇನ್ನೊಂದು ಚೂರು. ಹಾಂ ಸರ್, ದಟ್ ವಿಲ್ ಬಿ ಗುಡ್.
ಓಕೆ. ಅಸ್ಗರ್?
Good morning, everybody. I'm extremely happy to welcome you all to our today's National Science Day programs. As many of you may already know, Jawaharlal Nehru Planetarium conducts several programs throughout the year aimed at all age groups, starting from, say, 3rd, 4th standard up to BScs, undergraduate students and all. And many of these programs are sort of one-off, like our Sky Theatre shows or Know Your Star, science movies and all we have. And we also have lots of year-long programs. And this year, because of COVID situation, we could not conduct many of the programs. And thankfully, at least now the things have started looking better, and government has allowed us to do in-person programs also. And today we are having this program. We have lined up several programs today. One is, 2 lectures on gravitational waves. Slide changed. So on gravitational waves, and we all are extremely privileged that the second lecture, is by a scientist who has contributed a lot programs today. In the discovery of this and the progress of this field. 2 lectures, and on gravitational waves, we have a lecture by my colleague Madhusudan, whose talk you may have already heard earlier on different topics. He is an extremely talented teacher, and I'm sure all of you will enjoy his lecture, followed by lecture by Professor Bala Iyer himself. And this we at Jawaharlal Nehru Planetarium are very happy, Madhusudan, that this talk you may have already people who have played on different topics, pivotal role in the talented growth of this organization, have contributed immensely. Enjoy his lecture, followed by one is lecture by our founder director, Professor Bala Iyer, and today is the second speaker, Professor Bala Iyer. This I will not really go into we at Jawaharlal Nehru Planetarium are very happy. Madhusudan certainly be telling about their talk you contribution. Already people who apart from these two lectures earlier on, we also have pivotal role in the poster exhibition growth of this organization. Contributed immensely. Enjoy about various developments that have taken place. Lecture by our founder director, Science Bala Iyer, in the last 1 year, 1.5 years. Today is the second. We have Professor Bala posters on detection of earliest we at Jawaharlal Nehru Planetarium are very happy. Madhusudan certainly be telling about co-evolution of black holes and galaxies. We also have study poster exhibition growth of this organization contributed immensely in our enjoy rich program, and we have posters that have taken place. Lecture by founder Science in the last space mission and year 1.5 years. To Japan we have which brought posters on detection of earliest we at Jawaharlal Nehru Planetarium are very happy. Madhusudan lots of posters telling about co-evolution of people apart from galaxies. We also have study poster exhibition growth of our organization and contributed immensely in our enjoy rich program, and we have posters that have taken lecture by founder Science in the last space mission and year 1.5 years. To Japan we have which brought posters on detection of earliest we at Jawaharlal Nehru Planetarium very happy. Madhusudan lots of posters telling about co-evolution of
good morning to
people apart from
all of you who have assembled here.
study poster exhibition growth of our organization
Very brave people
in
have
our enjoy rich program, and we have
hopefully taken enough precautions to be on the safe side. Thank you immensely for joining us in person at the planetarium for this program. And we also take this opportunity to thank each and everyone. Good morning to the media platforms. All of you where this program is assembled here.
poster exhibition
Live.
very
Brave people joining us. Sunday morning is not a good time. Hopefully taken enough precautions. Many people on the same side doing some serious. Thank you immensely for hopefully we will joining us live and then planetarium. There will be enough light at the end of the program. And we also take this opportunity to thank. So today is National Science Day. Good morning to the media platforms. All of you where this program is assembled here celebrated National Science Day live and this year joining us. Sunday morning is not celebrating timely taken enough precautions. Many people celebrating doing some 5 years. Thank you immensely. But hopefully they will join me as I will arrange my planetarium. And there will be enough light at the end of the program. And we also take this opportunity. We have lined up so today is National Science Day. Good morning to introductory talks. All of you where Gravitational Waves assembled here. And that will be followed by live and this year talk by Sunday morning hopefully they will join me as I will responsible for rendering enough light at and we also have research scientists we have lined up so he will be talking today is National Science Day. Good morning to the introductory of gravitational waves and that will be followed by whole and in terms of astronomy talks by the three leaders in understanding many new light many people have released and 5 years is also observation responsible for rendering enough light basic gravitation fundamental ideas where research scientists have lined up so which is so he will be talking today about appreciating what is gravitation and why and long what scientific goals for waves astronomy talks by the three leaders in what are the basic new light many people have released technology basic offered challenge fundamental ideas which is direct so he will be talking appreciating what is gravitation and why long what scientific goals waves and the speaker is introduced in terms of what are the 5 basic introduce myself, and I will tell you what I am now. I am given the theory of what is momentum gravitation. So I'm not a subject technologist, right? It offers challenge fundamental because my only qualification is in the direct. So he will be talking along Ashia is what is close to listening to waves, great minds introduced in terms of what are the Bala introduced myself, and I will tell what I am now. I am given the theory of Barish. So I'm not a subject technologist, right? It offers challenge to discuss because my only various aspects of science, some of which will also be applied along Ashia is what is my only qualification is that listening to these ideas, and I'll try my best to show in terms of what are the Bala introduced myself, and I will tell what I am now. I am given so why is February 28th? So I'm not a subject technologist, right? It offers challenge to discuss only various aspects of science, some of which will also be applied along Ashia celebrate the announcement only qualification is that Raman listening to these ideas, and I'll try my best to show in terms of and you know that this also fetched him Nobel Prize in 1930, and it is not just a Nobel Prize in discovery. I'm not a subject technologist. Raman offers challenge to discuss obviously famous aspects of science, some of which will also on Raman spectroscopy celebrates announced key data radial investigation. Raman perhaps even listening to Raman would not have guessed how you know that this also fetched him Nobel Prize in 1970. It is not just a Nobel Prize in discovery, and it's the same story about gravitational waves. It offers challenge to discuss famous aspects of science. The founder of celebrates announced key data radial investigation. Raman perhaps even listening to Raman would not have guessed how you know that this also fetched him Nobel Prize in 1970. It is not just a Nobel Prize in years for detection and selection. The founder of now, gravitational wave astronomy is being, you know that very popularly referred to as the new astronomy. But the word new astronomy is not new. It has been used at least 2 times before in astronomy. One of them was when Johannes Kepler, studying the most difficult problem of his time, the orbit of Mars, the shape of orbit of Mars especially, which gravitational wave also led him to the formulation of the laws of planetary motion. So he published his work on Mars in a book called Astronomia Nova, which means new astronomy. It was new in the sense that people until then were only used to marking positions of planets, but now he had taken astronomy one step higher in terms of describing the motion of planets. So that was the first instance. And the second instance where new astronomy has been used is when spectroscopy was introduced into astronomy. So at the fag end of the table there, you see a small spectroscope sitting, very primitive and not so sophisticated, but it revolutionized astronomy in a way that again people who introduced spectroscopy would not have thought about. I mean, this is a recurring theme in science. Sometimes you make discoveries and you yourself do not know what the impact of a discovery will be 25 years, 35 years from that point. So Robert Bunsen and Gustav Kirchhoff, they showed that the spectrum of light coming from a source could be used to get information about the source itself, the mechanism by which light is being produced, and then what chemicals produce that light, and so on. And this has been beautifully applied in astronomy. One of the philosophers, I think it was Immanuel Kant, who said that human beings will forever be ignorant about the chemical composition of sun. I mean, it is so far away, you can't bring a piece of matter from sun to earth. it is impossible to find out what sun is composed of, because the normal way of finding the chemical composition is that you take a piece of matter to the laboratory, subject it to some chemical experiments, and you deduce what chemicals are possibly there. So at that time, the philosopher rightly thought that we would forever never know the chemical composition of sun or any star for that matter. But as they say, Professor Loknathan is very fond of saying this, and I would like to quote him: you should never say never in science. Okay, so just about 25 years from the time Immanuel Kant said this, spectroscopy came into existence, and there you see on the screen the spectrum of sunlight. And if you give this spectrum of sunlight to a scientist who understands this language, he or she will be able to tell you what chemicals are there on the sun, which chemical is in abundance, which is very, very rare, and what is the surface temperature of the sun, and even perhaps say how far the sun is. All this information is embedded in that ray of light that passes through the spectroscope that you see there, and you make it pass it through a prism, you get the spectrum, and the spectrum has all this information. In fact, I'm again borrowing a phrase from another great science popularizer and scientist, Carl Sagan, who talked about DNA being a library of information, because DNA stores all the information, genetic information that you have. Similarly, a spectrum is also a library of information. So any time that you have a spectrum of any kind, treat it not just as something that is colorful, treat it not just as something which gives you what different frequencies are present there in the spectrum. Treat it as a library of information. You get a whole lot of information about the source and the mechanism by which the spectrum was produced. So for a long time, light was the only messenger in astronomical or astrophysical situation, and people depended on this spectroscopic method to determine all the properties about celestial objects. So the advent of spectroscopy into astronomy was called new astronomy. So now we are on the threshold of one more new astronomy. Perhaps we just crossed this new astronomy era 5 years back when the first gravitational wave detection was made, and people are already talking about how new information that you would never ever get from light by studying spectrum of light, you would be getting by studying spectrum of gravitational waves. So that is something Professor Bala Iyer would be mentioning to you later on. So we take this opportunity to thank hundreds and thousands of scientists who have tirelessly worked for making this a reality, detection of gravitational wave a reality. It has not been a small task, as we will see, very difficult, technologically very, very challenging. It tests you to the extreme as an engineer. It tests you to the extreme as a theoretical astrophysicist. It tests you to the extreme as a computer analyst, data analyst, and so on. So everything is extreme as far as gravitational waves are concerned. So there is nothing like a simple way or simple path to understanding this. So we take this opportunity to convey our heartfelt thanks to all the people who have been part of this. And India has had therefore Einstein had talked about gravity, what their notion of gravity was, and then come to Einstein's notion of gravity, because of which gravitational waves uh, were thought to exist, and finally leading to detection of gravitational waves. But in going from Newton's theory of gravitation to Einstein's theory of gravitation, there are one or two subtle points which are extremely important, and I'm glad to see some students, young children sitting here. So these two subtle points will be in particular addressed to you. So gravity, as you know, is a fundamental force of nature. It's one of the fundamental forces of nature, and like any force, gravity also brings about acceleration. In fact, it was Newton who established this beautiful relation between force and acceleration through his second law of motion. And it is a common knowledge that if the mass of an object is large, then you need a larger force to accelerate to the same extent. Conversely, it means that if you apply same force to objects of different masses, the one with the least mass will have the most acceleration. But what about gravitational force? Especially when you think of objects that fall freely, when you drop objects freely, they are falling just under gravity. There is no other force acting on them, at least ideally no other force acting. Now, this would mean that heavier objects would fall faster than lighter objects, or would it be the other way? These are the subtle points that as young children, students of science, you should think about. So I'm just leaving some questions unanswered deliberately. Now this particular picture, Leaning Tower of Pisa, that is the iconic picture. So whenever you have to talk about falling bodies, gravity, then Leaning Tower of Pisa in the background will always tell you that you're talking about gravity. Okay, it's an irony because nobody did any experiment, at least in the beginning days, uh, to, to verify the result that I'm going to mention just now. So that is the great Galileo there on your screen. When he was a young boy, like many of you sitting here or watching on YouTube today, he was told that more massive objects would fall faster to the earth, like the picture on the left hand side. And as Galileo matured as a student of science, and then he started thinking independently, like all good students of science, he did not believe in what his teacher said. So he wanted to try out for himself. So what did he do? The right hand side picture is what Galileo is supposed to have done. That's a legend, that he dropped objects of different masses and he observed that they all fell at the same time. Okay. Therefore, the mass does not, the magnitude of mass does not matter as far as the gravitational acceleration is concerned. All objects accelerate at the same rate. This is highly counterintuitive, and especially if you have been told day in and day out as a student in your high school days, and suddenly you realize that everything that has been taught to you is totally out of sync with nature. That is the biggest revolution in your mind that you can ever experience. And Galileo is fortunate to have experienced many such revolutions. And one such revolution is this: he showed that it is just that all masses accelerate at the same rate. But he did not do this experiment from the Leaning Tower of Pisa as this picture shows, but he did it on by rolling spheres on an inclined plane. Okay, he was a very smart and intelligent person, a great experimenter. He used an inclined plane basically to reduce the effects of gravity. So in a sense, he diluted gravity for his experiments. And at lower accelerations, it was easy for him to compare the acceleration of different masses. And that's how he did that. So when he set the ball rolling, uh, he was also laying the foundation for a science of motion. But Galileo's work about motion of objects came to completion in a when Newton formulated the three laws of motion that you study in 8th, 9th standards. And through this mathematical approach, Newton was able to, uh, first of all, define what inertia is, the first law, And then through the second law, he told you how masses could be measured if you knew force or acceleration, one of them. So he established the relationship F equal to ma. And then there was this third law, which doesn't seem to have any kind of mathematical language built into it, when he says action and reaction are equal and opposite. Now this we take for granted, and actually it's a very tricky law. If you pay careful attention to the third law, it's very, very tricky. Now first thing you should ask is, why should action and reaction be equal and opposite at all? Okay, but then when you do experiments like everybody else does in the laboratory over small length scales, and when objects are in contact, you can be convinced that action and reaction are equal and opposite, and the forces are exchanged instantaneously. Only then the equal and opposite nature can be conserved. But as we shall see, this is the one which actually is the main difference between going from Newton's idea to Einstein's idea. We'll come to that in a short while. So Newton went on to do many things, but for today's presentation, his study of motion and gravitation are very important. So he formulated the law of gravitation. So in the simplest form, algebraic form, you see there on your screen. So it is inversely proportional to the distance, square of the distance, and directly proportional to the product of masses. Now the essence of Newton's theory of gravitation, this we need to know, because later on when we try to differentiate this with Einstein's theory, these features are very important. So number one, masses exert gravity, force of gravity. Then gravity is an attractive force. So unlike electrical charges and magnetic poles, you don't have attraction and repulsion both. It's only the attraction. But what is interesting is it can act through space and over astronomical distances. So you can have some system as large as the solar system or even bigger than the solar system, but there would be gravitational influence between objects that are placed at two extreme points of this huge length scale. So that is very important. And then, as an implication of the third law of motion, the gravitational force must act instantly from any point to any point. If action and reaction have to be equal and opposite, it is important that if there are two objects there, these two objects do not have any relative displacement in the time the force is communicated from one object to the other object. Which means force has to be communicated instantaneously in 0 second, which means infinite acceleration. Now, in Newton's time, that was accepted. I'm sure Newton also would have been a bit uncomfortable, knowing Newton that we know. He would have been uncomfortable with this idea, but still with this idea, he was able to explain a lot of phenomena, and there lies the success of this assumption. And also Newton's theory of gravity was extremely successful. Now the success of any theory is in terms of how many different phenomena can be accounted for and how well it accounts for. These two are the criteria to see if a theory is a good theory. So Newton's theory could be used to understand motion of moon, then motion of satellites around, multiple satellites around a planet, then all the hundreds of artificial satellites that we have launched to go around the earth. And some of you are watching on YouTube because of one of those satellites on the screen, which is helping you to watch this. So you should thank Newton's gravity for that. And then the solar system, entire solar system exists as a system held together by gravitational force on a large scale. Okay? But the crowning glory of Newton's theory of gravitation came when a new planet, Neptune, was discovered using the law of gravity. So they observed some irregular behavior in the orbit of planet Uranus, and they thought that this disturbance in the Uranus's orbit must be because of some other object being very close to it and exerting a gravitational force. And then they calculated from the perturbation of this Uranus orbit what should be the mass and what should be the position of the new object. Then people took a telescope and put in that particular position, and lo and behold, they actually found the object of the right mass in the right position. So what more do you want if you want a proof of any theory? So some unobserved phenomena has been uh, uh, unobserved object in this case has been discovered. So everything seemed to be going well. Oh, this is a very significant thing which I should not forget. Now, without going into the details, I can tell you that some of the effects of gravity can be artificially created or artificially nullified. You can cancel some of the gravitational effects under some conditions, and you can create some of the effects of gravity under certain other conditions. But there is one effect which you can never ever, Professor Loknathan has said, never say never in science, but this is one case I think I can take the liberty to say, but one effect of gravity which will never ever vanish is the effect of tidal force. So tidal force is actually a differential force. So if you take any object of a particular size, now the force of gravity acting at different points on that big object will be different, because the force of gravity is inversely proportional to the square of distance. So the distance is not the same to every point. Therefore, the forces are not the same at every point. Now, if you take the force at the center of mass of that object and the force at some other point on the object, and then you take the difference of these two forces, that force will never ever be zero, because the distance is not zero between the 2 points. You get that? Therefore, this differential force called tidal force is very important, and uh, that's a real signature of gravity, if we can say that. And tides on Earth is also because of this. And tidal forces are also seen on a grand scale, even at the level of galaxies and clusters of galaxies and so on. So tidal force is inescapable. You can escape gravitational effects somehow under certain conditions, but tidal effect of gravitation you can never get away with. So this is being emphasized by me only because it plays a central role in our theme of gravitational waves a little later on. So in summary, Newton's theory of gravitation coupled with his three laws of motion accounted for all the phenomena, and all the problems were solved in his time, astronomical problems especially. But yeah, this is what Einstein had to say. You found the only way in which in your age was just about possible for a man of highest thought and creative power. I mean, what a tribute Einstein is paying to Newton. And Professor Vishweshwara, about whom our director mentioned, whenever he quoted this, he would always tell the same words hold good for describing Einstein also. So you just take away Newton's name, put Einstein's name, and it is true for Einstein also. But one problem that Newton's gravity could not completely solve was this problem related to the orbit of planet Mercury. So planet Mercury's orbit is not in the same position all the time. The farthest point gently keeps shifting, as you see there. But unlike what you see there in the animation, the orbit is not closed on account of that. It is slightly displaced, the farthest point. So the orbit is not a closed orbit. So Newton's theory could not completely account for this. It accounted for most part of it, but not everything. So it still remained. So it was in this scenario that Albert Einstein works on a new theory of gravity, and he modifies Newton's theory of gravitation. He did not change it, he modified it. So the basic difference between changing and modification is that he in principle kept all the features of Newtonian gravity intact, but he added some extra dimension to that. Literally, he added an extra dimension to the theory by using special theory of relativity. He said it is not enough to describe in a classical fashion the motion of all these objects, and some new effects could be seen when special relativity is introduced to this. And the special relativity was introduced more as a necessity than anything else. So the new features of gravity naturally came out of Einstein's work. If Einstein introduced special relativity, and if he was still able to explain only what Newtonian theory explained, then it is not a great theory at all. But the greatness of a theory is when some new phenomena, some new behavior is predicted on the basis of this new theory. Plus, if some of the old problems which have not been solved by the old theory can be solved by the present one. So in Einstein's theory, gravity is not a force. Gravity is something that brings about a curvature of space-time. When we talk about space-time, we can only have hand-waving arguments like curvature of space-time, because nobody can either ever see nor can ever be visualized in any other fashion. So you can only have hand-waving argument, and if you are very fortunate to be working in this field, then there are Einstein's field equations which tell you what this curvature means. So you can only see in the mathematical equation, and in your mind you can never ever see physically. But then to visualize, some pictures like this on the screen are shown. So space-time is curved by gravity, and gravity is again a property of mass. Therefore mass curves curvature space-time. And second thing is that gravitational influences are not transmitted instantaneously. Remember action and reaction that I mentioned earlier? Now this action and reaction, by virtue of bringing special relativity into this, emphatically told that forces cannot be communicated, signals cannot be communicated, disturbance cannot be communicated in 0 seconds. There has to be some time delay between the source generating a signal and some other object or some other detector detecting the signal. There will be some finite time. Howsoever small, it will be greater than 0. Now this is the crux of Einstein's theory of gravitation, and as a consequence of this, gravitational waves naturally come out of general theory of relativity. Okay? Because waves are always produced by these disturbances as a function of time, they can propagate. There will be no waves if signals can go from one place to another place in 0 seconds. So this is the essence of gravitational waves and why they came into existence in theory. Now the first success of Einstein's theory was that Mercury's orbit, which could not be completely explained by Newtonian gravitation, could be exactly, precisely answered in terms of space-time curvature. So one old unfinished problem has been finished now, solution is completely given, therefore this is a better theory than the previous one, but only that would not make a great theory that general relativity is. Its greatness is that it predicts certain things which cannot be predicted in Newtonian gravitation, no matter what kind of mathematical treatment you give to that. So gravitational waves are impossible in Newtonian gravitation because forces can be communicated instantly. So Einstein proposes this gravitational waves in 1916, and the long road to detection, direct detection, took exactly 100 years because it was done in 2015 and announced in 2016. But the propounder or the proposer of this gravitational waves himself was very skeptical about the reality of gravitational waves. You know, many a times you get some mathematical solutions to a problem. That doesn't mean that the solution can be existing in reality. For example, if you are having a quadratic equation problem related to father's age, mother's age that you solve typically in your high school mathematics class, and suppose you find the father's age to be some t squared equal to 900, then you say t is equal to square root of 900, and you say father's age is 30 years. But you know that mathematically minus 30 is also allowed for that as a solution. But then you don't take minus 30 because it's impossible, and you say only what is real, and you take it as a plus 30. Similarly, whether gravitational waves are just mathematical artifacts or whether they can be real is another question. So Einstein doubted their existence. So that is the master himself telling about his opinion on gravitational waves. If you ask me whether there are gravitational waves or not, I must answer that I do not know. But it is a highly interesting problem. Now, this problem was highly interesting to Einstein because it challenges the theory to the extreme. But the interesting problem survived for nearly 100 years before it could be unequivocally uh, to be confirmed that this is true. So this is a good philosophy that Einstein proposes, and that's something as students of science we need to keep in mind, that you should not find a theory, you should not have a theory which works only on observable magnitudes. What he means by that is, if you have a theory which explains why this is moving like this and why this is coming around once in so many years and so on, this kind of a theory is just trying to explain what you are observing. That's not a great theory. You should have a theory in which the theory will tell you what you are supposed to observe. Okay? I mean, one grand example is Copernican heliocentric model. It was not just about taking away Earth and putting Sun at the center. Okay, in the heliocentric model. He said, if my heliocentric model is correct, like a good theoretician, Copernicus says, if you could improve the power of human vision, you will see that planet Venus must be showing phases, and planet Venus will have crescent phase when it is closest to Earth and full phase when it is farthest from the Earth. So this was a prediction he made. And Galileo's telescope, which actually improved human vision, the power of human vision, exactly did what Copernicus had predicted. So this is what Einstein is saying in principle, that theory should decide what we have to observe. So indirectly he's saying that I may not believe in gravitational waves, but then my theory says gravitational waves must exist. Now it is engineers and technicians and experimenters' problems to find out a method of finding out the existence of gravitational waves. Okay. So he also predicted several other properties of gravitational waves, because if you don't know the properties, then what are you looking for? What will you detect? And if you have to detect, you should come up with a method of detection. And the method of detection will depend upon the properties of the phenomena that you are trying to, or the description of the phenomena that you are trying to detect. So gravitational waves are actually transverse waves, just like light waves. So you have a certain direction of propagation which will be perpendicular to the direction in which the disturbance is made. So we have, I have a model here where I'll demonstrate that. Okay, so you have each and every segment of that model going up and down, but the disturbance itself is going from one end to the other end in a perpendicular direction. So that's exactly what happens even with that animation you are seeing on the screen. So if you have a circle of particles, and if gravitational waves are passing through that, then the gravitational waves will set up a disturbance. Gravitational waves will set up a disturbance in such a way that the particles are alternately stretched and squeezed, and that will be in a direction perpendicular to the direction of propagation of gravitational waves. Okay. And gravitational waves can also propagate in a slightly different plane, which is slightly 45 degrees away, which is 45 degrees away from the first one. So these are called the polarization states. Okay, so these are called the polarization states. And just in case somebody missed, this is again a demonstration of the transverse waves. So this polarization state is a term that you are familiar in the context of light. So it has the same meaning here. The polarization state will actually tell you the direction in which the wave is propagating. So light has two polarization states separated by 90 degrees, and gravitational waves have two polarization states which are separated by 45 degrees. So what do we mean by this? So these are two Polaroid sheets. So if they are parallel, it is transparent, you can see my face through this very clearly. The moment I rotate this by one of them by 90 degrees, then neither I can see you nor you can see me. It has become completely opaque. So light is not propagating through this when these are at 90 degrees. So these are two polarization states. But gravitational waves have polarization states which are separated by 45 degrees. And gravitational waves cause this kind of alternate uh, squeezing and stretching of matter, and how big the stretch is from the actual size of the object will depend on the size of the object itself. So larger the object size, then larger the difference in uh, the extra length by which it would have stretched. Okay. Now this has a very important, please bear this in mind, this has a very important consequence when we come to the LIGO detector later on. Okay, so LIGO detector is what you see on the bottom of the screen. This LIGO detector has two arms at 90 degrees. So something about the gravitational waves that I mentioned just now should give you a clue as to why it should be like that. And each arm is about 4 kilometers in length. So it's one detector which is 4 kilometers long. So longer the detector, the better, because gravitational wave effects would also depend on the size of the uh, detector that you are using. Of course, there are other factors on which it depends, which we'll come to a little later. But if you have to detect the gravitational waves, you have to first create them, or at least you should know under what circumstances these gravitational waves are created. So one general principle is that waves are always created by some kind of a disturbance in the source or in the medium or in both. So this animation uh, shows you a tuning fork which is vibrating. The vibrations are picked up by the molecules of air, and you see that the air molecules are also set into motion because of this vibration. They impinge on the eardrum, and the eardrum is actually set into vibration as a result of this. Now, what the eardrum does is to exactly mimic the vibrations of the tuning fork. Only then you can know what the tuning fork is doing. Otherwise, you have lost the signal. You have lost the information that is there in the tuning fork's vibrations. This is another very important idea, which is again useful in designing gravitational wave detectors. So whatever the detector, the eardrum of the gravitational wave detector, it should mimic the vibrations of the source which created the gravitational waves. So this is an analogous example. Now frequency is a property of the source. You can't take a tuning fork which is marked 216 and then set it to vibration at 512 vibrations per second. You can't do that. If it is marked 216, it is designed to be at 216. It's a property of that particular tuning fork. Similarly, when any source produces gravitational waves, the frequency of the gravitational wave will also depend on some parameter of the source. There is some parameter of tuning fork which restricts it to have a frequency at 216. Instead of restriction, maybe we can say that it fixes the frequency to be 216 hertz. Similarly, if you have gravitational wave of a particular frequency, then that frequency is the result of certain parameters of the object which is producing the gravitational waves. So that analogy works quite well. So one possible clue about the sources of gravitational waves is that they have to be astronomical. Okay, because gravitational force, whether it's in the Newtonian way or in the Einsteinian way, the space-time curvature, they're brought about by enormous masses. You and I cannot bring about any kind of space-time curvature that is measurable. In principle, yes, we may be, but then in practice, we will not be able to measure it at all. So you need huge masses, and such masses are found only in astronomical systems. Therefore, it is it is expected that some astronomical source will be the source of gravitational wave. But before we go to that and appreciate completely, a few measurable quantities about gravitational waves which are important for us. Let us just get to them. So one of them is the amplitude and the other is the strength. The amplitude is how much of a displacement could be there. In a pendulum, if you drag it to an extreme position from the mean position, that angular displacement gives you the amplitude. Now, the amplitude of a gravitational wave is given by this expression that you see on the screen, and immediately you will see that capital G, which is the universal gravitation constant, is in the numerator, and the denominator you have something like c to the power of 4. C is the speed of light. Speed of light is of the order of 10 to the power of 8 meter per second. So to the power of 4 is 10 to the power of 32. When that goes to the numerator, it will be 10 power minus 32. And gravitational constant is 10 power minus 11, order of magnitude. So you'll immediately see that amplitude is very, very small. So any change that you can make now in the amplitude that you detect is decided by that r, the distance from the object, which is in the denominator. So if the object is closer, you'll be fortunate to have a measurable amplitude, or that k, which is in the numerator, that will be related to the mass or the masses if it is a system of objects. That mass is going to decide how much the amplitude is. But again, for this huge 10 to the power of minus negative number that you get, to offset that by m, m should have a very large power. Okay. So gravitational waves are going to be of extremely small amplitude. So immediately tells you that any detector that you think about should be able to detect these very small amplitude. How much small is this amplitude? It will be of the order of 10 to the power of minus 16 to 10 to the power of minus 21 of a meter, which is about the size of a proton or a size of the nucleus, much lesser than the size of a nucleus of an atom. So the eardrum is much better than that, and even that sometimes we can barely hear. Therefore, all that you can hear from a gravitational wave is a whisper. You'll never hear a sound which is really going to hit the detector hard. Okay. And again, the energy carried depends on this frequency and amplitude squares of these two quantities. And you know that frequencies cannot be very large because these are astronomical objects which have to set gravitational waves into space, and having such a huge mass vibrating hundreds and thousands of times a second is not very easy. Okay, so you can expect gravitational waves to have very small frequencies and small amplitudes, but the energy locked in them is not small, because energy goes as c cubed by g, and c is now in the denominator and g is in the denominator and c is in the numerator. So you'll find that this has a very large number. The energy packed in gravitational waves is pretty large, though amplitude is very small. Okay, so these are some of the properties that we need to know, and in the next few minutes I'll quickly go over how the detection came to be. So the first source was expectedly from an astronomical of astronomical origin, but still I say it was an unexpected one because this kind of an astronomical source was not expected. Okay, and these are produced in the end stages of the life cycle of a massive star. So for our gravitational wave purpose, the top half of the picture is unimportant. Okay, but the bottom half, where a massive star goes on to become a supernova, and from there it goes on to become a neutron star or a black hole, these three events are very, very important because they are the major sources of gravitational waves as we know today. So, not surprisingly, the first gravitational wave, I can say the problem that was solved to perfection was in the context of a binary pulsar system. Pulsars are rotating neutron stars, so they periodically send radio waves in the direction of your plane of observation if you are lucky. If it is in some other plane and the radio waves don't cross your plane, then you will never know that there is a pulsar at all. So you have to be fortunate that it is going in a direction that your detectors can detect these radio pulses coming from them. And these two gentlemen, Hulse and Taylor, it's a long story once again, but we will cut it short. They discovered a binary system, that is two pulsars which are going around one another, and they were surprised to see a binary pulsar system in the first place. If I remember right, this is the first such system to be discovered. But what they discovered later on was even more interesting. They found that the time taken by these binary pulsars to go around a common center of mass, it was constantly reducing over a period of time, and it was reducing at a rate that could be measured by us. It was of the order of a few milliseconds per year, but still that was measurable. That is the precision we have in our experiments as far back as 1974. So they were able to show this. Now, if the orbit is shrinking, Kepler's laws of planetary motion will tell you that, first of all, when you have a fixed orbit like a planet going around the sun, it's a bound orbit, and the binding energy of this is negative. Now, if the orbit becomes smaller, then the binding energy becomes more negative. As a result, some energy has to be lost by the system in some form. Therefore, they thought that these pulsars, when they are actually diminishing in their orbital size, they should be losing energy in some form. But in what form? Now, this is where they make a guess that it could be because of gravitational waves, and they make all the back calculations, reverse calculations, and then they find that the rate at which the orbit is shrinking exactly matches when you assume that all that energy is going away in producing gravitational waves. So how much of gravitational wave is produced? What is the frequency? What is the amplitude? What is the gravitational flux that you find in that? Everything theory tells you how to calculate. Now you are making an observation here. What is it that you're making? You are measuring the time taken by a pulsar to go around itself in its orbit once. And you are seeing that it is diminishing with time. And using all these and a little more of general relativistic results, Hulse and Taylor showed that gravitational waves is most likely answer for this shrinking of the orbit. But this is not direct detection. This is like what the old Greeks would say, to save the appearance. So you make an observation and then you come up with an explanation. The explanation is more to tell you why you have made an observation the way you have made. So Hulse-Taylor pulsars calculations showed that gravitational waves could be the most likely candidate. But that doesn't directly tell you that it is gravitational waves. It could be a coincidence. However, their observation matched with the theory so well, you can see on this graph, the blue line is the theoretical prediction of a shrinking of the orbit if gravitational waves are being produced by them, and then the red dots are the actual positions which have been observed, and they fit so beautifully on the theoretical curve that it is most likely correct. So for this work, they were given Nobel Prize in 1993, I think. They were given the Nobel Prize. So what this experiment, observational evidence showed is that gravitational waves could perhaps be there in reality. So that brought in a lot of inspiration among people to set out to experimentally determine this. But I must tell you that the picture I'm showing you of Joseph Weber with a bar detector that he designed to detect gravitational waves, this was done even before Hulse-Taylor pulsar was discovered, okay, the 1960s. So experimental work had already started. So this bar was supposed to vibrate sympathetically at the same frequency as the gravitational waves, as the gravitational waves went through this detector. Okay, so I'll show you a simple experiment here. So you have two oscillators. I set one oscillator into oscillation, and you'll find that the other oscillator also is set into oscillation because they have the same frequency, natural frequency of vibrations. Okay, you see that? So with time, the bottom one picks up in amplitude, and that will also set up into, it will be set into oscillation. So this was the expectation of Weber, but he did not find any of them, and many others who tried to simulate, to replicate this also were not successful. But in experimental science, there is nothing like a failed experiment. No experiment is a failure. There can be some inadequacy in the experimental method, but no experiment can be a failure. So this was not a failure. It showed that this is not good enough. Okay, and the good enough one came later on in the form of LIGO. This is the LIGO detector I mentioned to you earlier. This is 2000 times larger than the bar detector. And we have seen that the tidal accelerations would be proportional to the size. Therefore, the expectation is that this detector would respond better than the Weber bar detector that we saw. And there were two detectors that were used by, there are two detectors which were set up in the US, one in Livingston and the other in Hanford. They're 3000 kilometers apart. So it takes about 7 milliseconds for light to go from one detector to the other detector. So it's not a small time, and it's a measurable time, by the way. 7 milliseconds may look like small, but actually it is detectable and measurable. These detectors were set up to detect gravitational waves. But then you should know what is it that you have to detect. What does gravitational wave look like? If you don't know how gravitational waves, what they look like, then you don't know what to detect. You know, many times it so happens that if I don't know what new thing is there in my work, I may be just rattling results one after another. I may not even realize that something profound is sitting there. To realize something profound is sitting there, my mind also should be prepared for it. In the same way, when the detector detects gravitational signal, gravitational wave signal, you should know what the signal should look like. And it is in this context that Professor C.V. Vishweshwara, popularly known as the black hole man of India, this is something that the press people gave when the gravitational wave detections were successfully done 5 years back, and he would actually laugh at this particular title given to him. So Professor C.V. Vishweshwara, way back in 1970, so this is between Weber's experiment with the bar detector and Hulse-Taylor pulsar's experiment, observational evidence. Professor Vishweshwara gives a theoretical uh, result which tells you what the gravitational wave signal would look like if it came from a collapsed black hole. Suppose you have a black hole, for some reason you disturb the black hole, you set into vibration, you roughly know the size of the black hole, mass of the black hole, you can calculate the amplitude and you can calculate the frequency. What would be the signal that would look like? This is a signal that would look like, and this is what people look for, or something similar to this is what they look for in gravitational wave detectors at LIGO. Okay, so again it's a theory which is telling us what to look for. Remember Einstein's quote that it is not enough to do science on observational magnitude alone. Theory should decide what you should look for. So Professor Vishweshwara's work showed for the first time what you should look for in a gravitational wave, what kind of a signal you should look for, and now it's a matter of collecting all the signals that the detector has detected and then have some kind of a computer algorithm from which you find out whether this signal is hidden in that. But it is not as simple as that. Professor Iyer will tell you, Bala Iyer will tell you what problems could possibly be there in doing that. It takes you the big data analysis to the extreme, but people have done it. That is the beautiful thing about this. Okay, so The arms are very large, and so that gives you a big tidal acceleration. And then at the end of each arm is actually a piece of glass of a very high quality, which is suspended from a fiber, and this whole system is isolated from local vibrations, because this glass should be so sensitive that it will vibrate when gravitational waves pass through it, but it should not vibrate when you and I walk next to the detector. That amplitude will be several times more than the gravitational wave amplitude, so it should not respond to these things. So you should know what is a spurious vibration, you should know what is a gravitational wave signal. So that has been done, and the basic principle on which it works is shown here. So light is now, laser light is going in two perpendicular directions along the two arms of LIGO, setting the two mirrors at the ends into oscillation. But the beautiful thing is that the two mirrors do not oscillate in phase. So while one is going away, the other is coming closer. So this is what we mean by the tidal acceleration. And what it does is, when finally light comes after reflection from these two mirrors, there would be a constructive interference, and you see the signal. So at all times it would be set to dark. There will be no light on the screen. So if there is any disturbance in the mirror, suddenly you will see some light because of constructive interference of light. And that can happen only if gravitational waves have caused some disturbance there. And by how much does this this mirror set into displacement? It is of the order of the diameter of the proton that we mentioned earlier. So that is the precision that you need to set up this experiment. So Professor Vishweshwara had worked out in the context of gravitational sources, black holes as a gravitational wave source. Whenever it collapses from some asymmetric form to a symmetric form, as long as this asymmetry is there in the black hole, there will be radiation of gravitational waves. The moment it becomes a perfectly spherical one, such a source will not produce gravitational waves. Again, general theory tells you that. So that is the reason why in the gravitational wave form, so this is not the gravitational wave that is actually detected, this is a mathematically generated one, but pretty similar to this. I am showing this for the sake of clarity. So you'll see that as the LIGO detected the first one, that it was actually in the case of two black holes going around a common center of mass, and you'll find that with the time, the gravitational wave amplitude is gradually increasing. It becomes a peak exactly when the two black holes merge, and immediately after merging, there is a decay in the amplitude. This is because now the black hole, which or the two black holes going around one another, there's some asymmetry there, which was actually producing the gravitational waves all this while. And then when the single black hole was formed by the merger, the black hole became such a wonderfully symmetrical object that it stopped producing any gravitational waves, and whatever this decay part that you see in the wave is like what is known as a ring down. That's called a ring down. It's like a bell. You strike that, the amplitude goes down with time, but the frequency remains the same. That's exactly what happens here. There are two parts to this signal. On the left part of the peak, the amplitude is increasing, frequency is increasing. But on the right part, frequency is constant, but the amplitude is decaying. So this is the pattern that Professor C.V. Vishweshwara's work predicted, and this is the basic idea that goes into finding out whether gravitational wave signal is embedded whenever this mirrors in the LIGO are displaced. But different kinds of sources are there now. Not just black hole mergers. You can have an event in which a black hole is formed, as in the case of a supernova. So for a small time, the black hole would most likely be going from an asymmetric geometry to a symmetric geometry, and in that period, there will be gravitational waves that will be produced, and there would be neutron stars that could merge. There could be a combination of neutron star and a black hole that could merge. So various combinations are there, but essentially these are all astronomical sources. These are all very, very compact objects like black holes, neutron stars, and so on. And once you detect, I mean, you have spent billions and billions of rupees or dollars to set up the observatory like LIGO, and then once in a while you find a signal passing through that and you detect the signal, and then you do all the calculations. What does that wave contain? Remember that spectrum of light, library of information. So this is the library of information of a gravitational wave. So from this gravitational wave signal, you can find out what was the source, how far was the source, and what was the mechanism by which gravitational waves were produced, and for how long was it produced, what were the masses of the two objects before they merged, and what is the mass after they have merged. It's literally a library of information. And these kind of numbers are extremely important to build models, mathematical models about not only gravitational waves, but also about the objects and the mechanism by which they have been produced. So, 5 years back, what happened at LIGO was a direct detection of gravitational waves. This also directly showed that black holes also exist. Okay, so it was not a circumstantial evidence like it had been all along. So now we know that both black holes exist for as a real thing, and gravitational waves also exist as a real thing. Therefore, all is well that ends well. But then it doesn't end here, the story. The story continues, and that story will be continued by Professor Bala Iyer after a short break of about 5 minutes or 10 minutes. So if you have to just go out and come back, so please be back in 5 minutes time. And as soon as Professor Bala Iyer's lecture is set up, you'll be watching him on the screens here. Okay, and after the talk, we will you can have your questions. We will have Professor Bala here take up at least a few questions to answer at the end. So thank you very much, and so we'll have a short break and we'll come back. the important results that have been gathered over the last 5 years through these gravitational wave detectors and how these results are important and what the future of gravitational wave astronomy will be like. So I'll have a very brief introduction, which is the most difficult part actually. Elaborate introductions are always very easy. Professor Bala Iyer is currently a Simons Visiting Professor at ICTS TIFR Bangalore, and he is the co-principal investigator of the LIGO India Scientific Collaboration. He completed his BSc, MSc and PhD from Bombay University. He was in the Raman Research Institute, Bangalore during 1980 to 2014 and worked on astrophysical applications of general relativity, perturbation methods, and black holes. Since 1990, he has worked on calculations of gravitational waves from inspiraling, of course, inspiring also is an apt word there, inspiraling binaries of neutron stars and black holes. He is a fellow American of American Physical Society and International Society on General Relativity and Gravitation. He has been chair of the Indigo Consortium from its inception in 2009 and was the principal investigator of Indigo participation in the LIGO scientific collaboration during 2014 to 2019. He was a member of the core team of LIGO India mega project proposal. He is a chief editor and subject editor on gravitational waves for the online journal Living Reviews in Relativity, which is published currently by Springer. Professor Bala Iyer has been a visiting scientist in France, UK, Germany, USA, and so on. He has been involved in research education advancement program for BSc students at the Bangalore Planetarium for over 2 decades. I think involved is really an understatement. Professor Bala Iyer has been the pillar source of inspiration and the person who is primarily responsible for the REAP program in the planetarium, which has seen hundreds of students take to scientific research and some of them into gravitational waves as well. And over the last 2 decades, he has been associated very closely with planetarium and its activities, and public outreach on general relativity and gravitational waves is another activity that he is very passionate about. So we are very fortunate that Professor Bala Iyer has joined and to give this talk, because he has been in the forefront of gravitational wave research, and when it comes to the first detection of gravitational waves, his theoretical work, calculations especially, have played a central role, and we are fortunate that he is here today to share with us the results of last 5 years of gravitational wave research. So thank you very much, sir. And now I request you to take over and conduct the talk.
Okay. Thank you, Madhusudan, for the kind invitation, and all the audience who have, as you said, braved to be there in the planetarium, and all the others who on a Sunday morning are listening on YouTube. Thank you also, Madhusudan, for a very nice overview, bringing us from the times of Newton, Galileo, Newton, and then finally coming to the detection of gravitational waves. Now, before I begin my lecture, as you know, since we talk about pedagogy, you have really covered a lot of material. So I'll begin. Yeah. Hello. Hello. Can you hear me? Hello. Can somebody confirm whether the audio is there?
Yes, sir. It's very clear.
Okay. No, somebody said audio is a problem. Can I go ahead?
Yes, sir. Please, sir. YouTube.
Okay.
The
So.
YouTube also, it is very good.
Okay, very good. So let me begin. So I begin by, whenever you are in a train, when the train starts going ahead, it sort of goes back a little and then goes ahead. And the first part of my lecture, for a few tens of minutes, would really be in that particular spirit. trying to remind you about the highlights in Madhusudan's lecture. So I call that particular part gravitational waves from A to B. The detection of gravitational waves is celebrated as one of the greatest scientific achievements of all time. And for this reason, the Livingston Observatory and the Hanford Observatory have been declared in the US as historic physics sites. I hope to convince you that this is not an overstatement by the end of my talk. As Madhusudan remarked, discovered in 1974, the binary pulsar 1913 plus 16 led to the Nobel to Hulse and Taylor in 1993. This was a watershed event in our story since it demonstrated that gravitational waves are physical and accurately described by Einstein's general theory of relativity. It should be emphasized that this Nobel Prize was not for the discovery of gravitational waves, but for the discovery of a new type of pulsar that opened up new possibilities for the study of gravitation. That means to precisely try to check for predictions of Einstein's general theory of relativity. Such systems, after a few 100 million years of inspiral, would coalesce in the last few minutes, emitting gravitational waves at frequencies where laser interferometric gravitational wave detectors which were being designed at that particular time were exactly sensitive. This is the important point, that you discover something and that discovery in radio astronomy has implications for something else, which was the search for gravitational waves. Now, as Madhusudan explained, the interferometer essentially acts like a transducer, which basically converts the gravitational waves to a photocurrent, which is proportional to the strain amplitude. But as he emphasized, you really need to beat a number of fundamental and technical noise sources that affect measurements at subnuclear length scales. You are trying to measure in a system which is a few kilometers long a displacement which is 1,000th of the size of a nucleus. And this is made possible because of all the technology and all the advance in physics which really has happened. For example, at higher frequencies, the sensitivity is achieved because of using high laser power. At the mid frequencies, it is achieved by using lower thermal noise mirrors. And the biggest challenge is at the lowest frequencies, because even though we think we are sitting on a very stable Earth, the Earth is really being moved because of seismic motion. So the seismic motion has to be damped by factors of 10 raised to 10 or so on. And therefore, by using shock absorbers, which are called active and passive isolation systems, you can really damp all those motions and get to the sensitivity which you really require to make a detection of gravitational waves. So this is the main point. This is the technological challenges which really makes it a very challenging experiment. The whole interferometer is a very large vacuum system at ultra high vacuum. It's a very complex system, and you really need about 300 control loops to make the interferometer optimally running. All this really involves instrument science at the frontiers of physics fundamental limits. As Madhusudan mentioned, you need the experiment, only one thing to go wrong for the experiment to fail, but you need hundreds of things to go right for the experiment to succeed. And that is really why, in a sense, Einstein could not believe this could ever be done, and it really required all the progress of the 100 years to really make the first detection of gravitational waves. The other kind of challenges basically come because of the nature of these particular sources. Even though we are looking at gravitational waves from neutron stars and black holes, they are weak signals which are buried in the large noise of the detector, and therefore you require engineering techniques like match filtering, both to detect this particular signal and eventually to estimate the parameters of this particular signal or how to characterize this particular signal. To do this, you use a technique which is called match filtering. What is match filtering? You basically correlate a known signal with the noisy data. That means you multiply the noisy data by a known signal and you integrate as is shown in this particular animation. So when you do this correlation, even though the signal is very small, when you look at the correlation, when you match you can see that In general, the correlation is very small, but when your template matched exactly with whatever was buried in the noise, the correlation was basically picked up. So the important point is you really don't know the parameters of this signal, and therefore you cannot do it with only one template. You really have to create a bank of templates. Thousands of templates are really required, and this is where the challenge of computing really comes about. Also, for example, if you don't have the correct phase information, you will not be able to pick up the correlation as strongly as you see on this particular graph. Therefore, you really need a very accurate model of the signal using the best theory of gravity, and the best theory of gravity, as Madhusudan explained, currently is the general theory of relativity. Now, when you try to calculate the gravitational waveform for self-gravitating bodies, you come up with a technical complication. Remember, when you learn when you, for example, learn special relativity, you learn that you have a leading order Newtonian prediction, and then depending on the value of V by C, you have higher order corrections. So you'll have the V square by C square correction, V4 by C4 correction, and so on. If you want to calculate the corrections to Einstein's prediction, you really need to calculate what are called higher order corrections to the Einstein formula. But when you have a self-gravitating body, the higher order correction, the V square, is of the same order as Gm by R. This is what is called as the virial theorem. So if you want higher orders of V square, you really need to have higher orders in G. That means you have to work with the nonlinearities of Einstein's equation. The simple linearized gravity which Einstein used is not enough, and that is really the big challenge which really faced all the theoreticians. But when the binary pulsar was discovered, this problem needed to be addressed, and therefore the techniques which were invented during the analysis of the binary pulsar came into maturity in the 1990 in the 90s, when the LIGO detector was really created. So what is shown in this particular formula is the gravitational wave phase, which is given. The first term which you see outside is the Einstein prediction, and every subsequent term is a correction in V square by C square. So you can see here that you really have to improve the calculation to V7 by C7. And the interesting thing is that Einstein's theory of relativity can be perturbatively calculated to really calculate these numbers. If you look at this particular formula, in each of these particular orders, you see very, very large kind of numbers. These are precise predictions from Einstein's general theory of relativity. So if in some sense you can look at the waveform, you can try to measure the correctness of Einstein's theory, which is what I will show you a little later. This complicated formula is the simplest formula, because this formula applies to what is called as the inspiral phase of when the body is moving at relatively smaller velocities. But when it comes towards the end of its inspiral, this body, the approximation which you are using essentially breaks down, because you are going to higher values of V by C. So you really have to extend the domain of applicability of this particular formula, and there are mathematical techniques called resummation, and therefore you have to really extend your post-Newtonian perturbative calculations by techniques which are called effective one body, by using numerical relativity, that is numerical relativity solutions of Einstein's equations, phenomenological waveforms, using techniques like replacing the complicated waveforms by its surrogates. So there is a very large body of theoretical work which really is required so that you can model this waveform very, very accurately. And why do you need to do that? Because if you don't know the waveform very accurately, you will not be able to do match filtering, and therefore you will not be able to be sure that you are really seeing the signal which you are claiming to see. So once you have the raw data, to really look at the signal, you really have to go through a very complicated process of calibrating the detector and then characterizing all the noises in that particular detector. And after doing this complicated thing, which is really takes probably sometimes a very large number of people, a large number of time, months, etc., you come up with the signal which is shown here in blue. And then, as I told you, we know that the parameter really depends on the many parameters. For example, the signal will depend on the mass of that object, the angular momentum of this particular object, how far it is, where it is located in the sky, what is the orientation of the source relative to the detector, what is the time at which the signal reaches the detector, what is the phase when it reaches the detector, and so on. So there is a 15 parameter dependence of the waveform which your signal picks up, and what you really have to do is look at the signal and then try to ask, by changing the parameters, what is the final parameter which comes closest to this particular signal which you are basically seeing. So essentially, after detecting this particular signal, by doing this kind of analysis for all possible combinations of these 15 parameters, you can calculate what is the parameters which describe this source. Remember, it's a statistical process, so we cannot be 100% sure. So what we really come up with is what is called as statistical Bayesian methods, which basically tells you with 90% confidence my signals is given by these particular parameters. So you can see here a lot of statistical analysis, a lot of numerical work underlies this particular detection. Now, the sources, as Madhusudan mentioned, could be either a black hole. Now, if it is a black hole, there are many effects on that particular black hole. For example, if the black hole is spinning, it will have some implications for the waveform. There are nonlinear effects called tail effects. If it's a black hole, the horizon absorbs radiation. And finally, there are the quasi-normal modes. So in the complicated formula which I showed you, all these physical effects are basically buried. But it's a very definite prediction of how the waveform should look like given all these particular parameters. If, on the other hand, you are talking about a neutron star, this object is not as rigid as a black hole. So though in the beginning it will look like as if it is a black hole, as the bodies come closer to each other, they start distorting each other. So the waveform starts departing from the black hole waveform, and therefore, depending on the equation of state of the material which makes up this neutron star, the final waveforms will be tidally deformed. So by looking at the tidal deformation which this waveform undergoes, you can say something about microphysics. You can say something about the equation of state which the neutron star matter is really made up of. So you can see here that it is not just doing astronomy, it is also doing fundamental physics which you can extract out from this particular astronomical observation. Madhusudan also sort of mentioned to you that the properties of gravitational waves are inferred from the theory of gravity. So for example, all the properties of gravitational waves which he mentioned really come as predictions of general theory of relativity. For example, one can show from Einstein's equations that gravitational waves travel at the speed of light, they are transverse, and they have two states of polarization. Unlike electromagnetic waves, where you have dipole radiation, in gravitational waves, there is no monopolar dipole radiation, and these are related to fundamental properties of conservation laws for energy, linear and angular momentum, which the gravitational field will satisfy. So once you can say, what is the nature of this particular gravitation, you can test Einstein's general theory of relativity. There are big differences also because of the fact that the gravitational interaction is very, very weak compared to the electromagnetic interaction. So the gravitational waves propagate unperturbed through space because they interact very, very weakly with matter. Remember, the gravitational interaction is about 10⁻39 times weaker compared to the electromagnetic interaction. So the important point is that if you cannot see electromagnetic radiation from the heart of a supernova or from the beginning of the Big Bang, but the gravitational waves can come from almost the creation of the universe. So the important point is that you can see gravitational waves from inside of a supernova or from the beginnings of the Big Bang itself. And as I explained to you, that the properties of gravitational waves can be different in different theories of gravity. So eventually, if you can measure the properties of gravitational waves, you will be able to test general theory of relativity. So this is again to emphasize what Madhusudan told you, that you begin at some particular point, but that is not where you end. It sort of creates a revolution much beyond where you sort of begin with, and this is how science essentially proceeds. So I just want to end my small presentation by emphasizing that it is this experiment, a very complicated experiment, which is driving theory. There is a very exquisite theory, which is the general theory of relativity. You can use it to describe astrophysical objects like black holes and neutron stars. And it is this theory which underlies the efficient and sophisticated data analysis infrastructure, which today is possible because of the state-of-the-art computing. As I told you, you have to construct template banks for detection and use Bayesian methods so that you can send alerts to your astronomy colleagues and inaugurate multi-messenger astronomy, about which I will talk in the later part of my lecture. And as I explained to you, you do parameter estimation both online and offline. And from this parameter estimation, you can reconstruct something about this particular source and eventually describe or discover new astrophysics, new cosmology, and eventually try to even test Einstein himself. So remember, we are coming up with a prediction of gravitational waves from Einstein's theory of relativity, but the predictions, the experimental confirmation or not, really comes from the experiment. So ultimately, Einstein's theory will itself be tested by the prediction which the theory itself made. So this essentially finishes my, Einstein's gravitational waves A to B. And now I essentially come to the discoveries which the LIGO and the Virgo collaboration really has made. So I have to sort of emphasize, as Madhusudan mentioned, that this is what I'm going to tell you in the rest of my talk is the work of not a single individual, but of a very large collaboration. In fact, two collaborations, the LIGO scientific collaboration and the Virgo collaboration, and more recently the Kagra collaboration, which is the Japanese collaboration. It has thousands of individuals, close to about 2,000 people, and therefore all this work essentially was basically possible because in addition to high quality experimentation, a high quality of theory, what is really required is a modern paradigm for doing research, and that is bringing in a large number of people, because of the fact that many things need to be investigated. There is a complex parameter space to be investigated, many things to be done, so a simple single laboratory cannot sort of do it. Integrating a global community was really required, and this was the strategy which the high energy physics or the particle physics people had put in place, and bringing in those ideas in gravitational wave physics really led to this particular discovery. So let's begin with the first detection of gravitational waves. The first detection of gravitational waves happened in the first observing run of the advanced LIGO, which began on September 12th. It was a 4-month-long effort, and almost a couple of days after the instrument was turned on, the two LIGO observatories in Hanford and Livingston detected a coincident gravitational wave signal. Remember, because we are looking for something very, very sensitive, if you just saw it in one particular detector, you would not know whether it was because you sneezed in the room or because a black hole went off somewhere in the universe. So to be sure, you just want to make sure that you see it in two different detectors. So again, you saw the detectors in the two within 7 milliseconds, and it was a very loud signal. So we say that it has a large signal to noise ratio. This is what is basically shown. So suddenly you can see in this time frequency region, region lighting up, and then this lighting up essentially is for a very brief period, you are seeing a burst of radiation. Something is causing the interferometer, the photo detector to give, a particular signal. And remember, the waveforms have a particular profile, and if it is from the same source, the profile should be very similar, modulo the differences which can come from the instrument itself. And that is what you have to look for. But remember, there can be a time lag. So essentially, you should be able to move one waveform relative to the other, and then they should essentially match with each other. And that is essentially how you look for astrophysical signal. So this is our famous picture that we have the observed data. Once you have the observed data and you shift it, the signals fall over each other. I also explained to you how you can extract out the parameters of this particular signal. Once you have the parameters, you can do numerical relativity and reconstruct from Einstein's equations what the expected signal should look like. And then if you subtract out from the observed data the expected signals, then what you should be left with is only the residuals, which does not have any new physics, but it should be only due to the noise of these particular detectors. So this is essentially why we basically think that we have really seen a signal from an astrophysical source. And as you can see here, it's a very loud signal. We only saw about 8 cycles. The signal lasted for about a fraction of a second. But the important point is we seem to be very, very confident that we are seeing an astrophysical signal. Now it's very interesting that the signal was so loud that we really didn't need to do match filtering. But somewhere in December, a second signal was sort of seen, which could only be detected because of match filtering. And that essentially, made us confident that we are really, everything which we have put together is essentially working. So then I explained to you in my previous summary how the parameters can be extracted. So you found the mass of the two black holes, the final black hole mass. And if you see the difference, you see that there are 3 solar mass worth of material being converted into gravitational radiation. You can find out the final spin of the black hole. You can find out how far it is. And by assuming a standard cosmology, you can calculate what is called as the redshift of this particular object. So you can see here that in all my rest of my talk, you will find that this is exactly what I'm doing. So I gave you that summary in the beginning because that summary underlies everything which I'm going to tell you from now on. So I'll only focus on what the conclusions are in each of these particular cases. So as Madhusudan explained, this was the first detection of gravitational waves. It was the first detection of a binary black hole that merges within the age of the universe. Remember, before this we had seen binary neutron stars, and therefore we had conjectured that there could be binary black holes in the universe. Nobody had conclusively seen a binary black hole, and you were not sure that even if a binary black hole existed, whether within the age of the universe it will merge. So we have really seen that in the first discovery itself. Before this, nobody had seen stellar mass black holes of such high masses. Black holes were seen by electromagnetic observations, but as I will show you a little later, their masses were always much smaller. Now, the moment you really want to create a massive black hole, it tells you, what is the environment in which this black hole was really formed. Because when you try to make a black hole, there is this effect of stellar winds. And if the stellar winds are very large, the black hole found will not be very, very massive. So obviously, because you're seeing a massive black hole, the stellar wind is very weak. And the dependence of the stellar wind is on the chemical composition of the material which makes it up. So it tells us that the metallicity of this particular medium is very, very small. So you can see here that detailed information of astrophysics is coming from this simple discovery of this particular gravitational wave. And then, as I told you, once you have a system like this, you can start questioning whether Einstein's prediction of the waveform is correct. And remember, by the time these objects are merging, They are moving at very, very large velocities. The gravitational field is very, very strong. So you are testing the general theory of relativity in regimes where it has never been tested before. So you can see here that it is far from being only the first direct detection of gravitational waves. It is telling us a very rich amount of astrophysics and physics. And then, as I told you, the gravitational waves is coming from a binary black hole system at a very large distance. It was emitted 1.3 billion years ago. And if you wonder what was happening on the Earth when you at 1.3 billion years ago, forget about human beings being there. We were in a phase in biology when on the Earth a single cell was advancing to a multicellular form of life. So isn't it very amazing that an event which happened so far away, about that we can make such very, very precise prediction. That is the power of gravitational wave astronomy, which really came into being almost at its first discovery. That is the amazing thing, as you will see. And as Madhusudan explained, in this discovery paper there were 37 authors from Indian institutions and citations to the seminal papers which included Indian researchers. One of them also being the paper by Professor Vishweshwara. So I would like to sort of emphasize that in 1919, on November 7th, with the eclipse experiment, Einstein became a worldwide celebrity, because all the newspapers on that particular day had only something about the eclipse experiment. We were very fortunate that on February 11, 2016, we were alive. And if you looked at the newspapers all around the world, it was about a scientific discovery and not about whether one particular party was doing something or something like that. So it was a amazing feeling on that particular day, and we should be very feel very fortunate that we were part of that excitement. And of course, what more would Einstein want on this centenary? Remember, as Madhusudan explained, it was 100 years for general relativity, 100 years for gravitational waves, and Einstein is still right. The predictions which he made are exactly verified by the experiment which really happened, or the observations which really happened on that particular day. It's very interesting that for us it had a very important consequence, because just a week after the announcement of this discovery, the LIGO India proposal was approved in principle by the government. The LIGO India proposal was made in 2011 by the Indigo Consortium, which was formed in 2009, but the approval was pending. This discovery immediately hit the headlines, and the approval really happened. So it is very, very important that when you make the astrological charts, you really have to put in the black holes also, so that you can predict what really happens. When will LIGO India happen? Currently, we think that LIGO India will become operational by 2026. Why is LIGO India important? It's important to emphasize that interferometers have a broad directional response. The interferometers are not like eyes, but like ears. Because remember, when you have your ear, you can hear from all around. Whereas if you see, you can see in one particular direction. So the single detector is not it's not like a telescope. So if you really want to know where a gravitational wave is coming from, you need to do localization. And for that localization, you need a global network of gravitational wave detectors. And when the first generation of gravitational wave detectors became successful, people did the study and realized that the localization of sources, if you use only the LIGO and Virgo detectors, they are not good in certain parts of the sky. The localization is poor. On the other hand, if the detector is in India, the localization is good over all the parts of the sky. And therefore, a quantitative study indicated that if you include LIGO India, it would improve the angular resolution on an average by 4 times, and in some directions, as you can see, by factors of 10 or 20. So it is very, very important that in the future, if you really want to do multi-messenger astronomy, LIGO India can play a very critical role. On October 3rd, 2017, the Nobel Prize was announced, and it went to the three people, Barish, Thorne, and Weiss. And if you really look at the citation, it basically says, for decisive contributions to the LIGO detector and the observation of gravitational waves. Broadly, the experimenter was Weiss, for whom, because of which he got half the Nobel Prize. The person who pushed the theory part was Thorne, and the person who pushed for the collaborative model for doing research was Barish. So essentially, three different aspects was recognized by this Nobel Prize, and it is very interesting that just a couple of years. So remember the Hulse-Taylor Nobel Prize. The Hulse-Taylor was discovered in 74. The Nobel Prize came in 1993. On the other hand, in this particular case, in a couple of years, the Nobel Prize was given. And remember, it really is a culmination of work which happened for almost 40 to 50 years. So it is a very interesting sort of sociological thing that the proof was accepted by the Nobel Prize very, very quickly. The second observing run of LIGO started in 2016. It was supposed to happen for a longer time. So the strategy always is make the detector more sensitive so that you can see further in the universe, and run the detector for a long time so that you can look for more events. So this observation run began initially with only LIGO, but in the last month, the Virgo detector also joined. Interestingly, just in a fortnight, the first detection by the three detectors, Hanford, Livingston, and Virgo, really happened. And it sort of proved what we have been always sort of saying, that when you looked at the sky localization, if only the LIGO detectors were operational, the sky localization covered about 1,000 square degrees. Whereas if you use the information from the Virgo detector also, the 1,000 degrees dropped to about 60 square degrees. Also, because you have more detectors, you can try to test for the nature of the gravity wave polarization, and one could show that the observations were consistent with the Einstein's tensor, the two states of linear polarization, which Madhusudan explained in your lecture. So you can see here that the moment you put in a new detector, extra information which was not possible with only the earlier network, comes into being, and this was amazing. In 2 weeks, we have a new paradigm for astronomy. This was very important for what I'm going to say next. For example, I told you that the Nobel Prize was announced on October 3rd, but the full community was desperately waiting for something else, an announcement which happened on October 16. And this is what I call the spectacular launch of multi-messenger astronomy. I'll try to show it to you in this small video. You are now having two neutron stars which are going around each other. These neutron stars coalesce, put out gravitational waves. Those gravitational waves travel, reach towards the Earth, make it ripple. About 1.7 seconds later, gamma rays discovered by Fermi, and 11 hours later, optical observation really essentially happens. So you can see here that this is what is meant by, I'll go over the thing again because it's interesting. In spiral, coming close, merger, coming close to merger, merger radiation, gravitational waves reaching the Earth, LIGO, about 2 seconds later, gamma rays, and 11 hours later, optical radiation from that same region in this particular sky. So this is essentially what we call as the possibility of multi-messenger astronomy triggered by gravitational waves. So in a sense, gravitational wave detectors are like lighthouses in the universe. They are always on. They can see radiations from any part in the sky, and once you get radiation from there, that alert can be sent to other astronomers, and the astronomers can look for radiation from that particular source or that particular region in the sky. So in more detail, what is shown here is the waveform, and as you can see here, the waveform is very large. It was detected, as I told you, you could not detect it by just like that. If you just saw the output of the detector, you will not see anything. But if you use match filter, you remember the complicated formula which I gave you that in the beginning, the complicated formula describes the inspiral, and using filters constructed by that particular formula, you can show that this waveform trace which is shown here can be exactly predicted. There are not just 8 cycles but 4200 cycles, and the signal lasts for about 100 seconds, and the signal to noise ratio, because you can see it integrated for 1000 seconds, is larger than that black hole signal. So the important point is you have been able to see the gravitational wave signal, but what really made it exciting is what is shown here, that the gravitational wave detector is being seen in LIGO. At the same time, the Fermi satellite, which looks for gamma ray, sees a signal 1.7 seconds after that. So you can see here that maybe it is a coincidence, maybe it's an accident. So you really have to make sure that the gamma ray signal and the gravitational wave signal is from the same source. So what you do is you send a warning to the astronomers, and they start looking at that particular region in the sky. But then remember, the location in the sky should be very precisely given to them. And as I told you, if you had only the LIGO detectors, you would find that the localization in the sky is a very large ellipse. On the other hand, the moment the Virgo detectors came, 17814 and 17817, the sky area is very, very small. So the astronomers can more efficiently look for radiation from those parts in the sky. So this is why the sky localization is a very, very important thing. And we were very lucky that the Virgo detector had come on, and therefore the sky localization for the neutron star source was very, very small, and therefore this information was passed on to the astronomers, and 10 hours or 11 hours later, this telescope really looked in that particular region in the sky and saw an optical counterpart. The moment it saw it, 5 other observatories could confirm it, that in that region in the sky there was an optical radiation. So the important point is that this object, the information about this particular object was passed on to 70 observatories. There were about 100 instruments, including 3 Indian instruments, the AstroSat, the GMRT, and the Himalayan Chandra telescope. The first one an X-ray mission, the second one a radio astronomy facility, and the third one an optical facility. All these were looking in this particular region in the sky, and what is shown here is that a collection of Earth-based telescopes and space-based telescopes try to look for this particular object. So what is shown here is the radiation in gamma, in gravitational waves, gamma ray, X-ray, ultraviolet, optical, infrared, and radio. The X-ray radiation came after 9 days, the radio after 16 days, and all these different timescales really come because of the fact that the physical processes which lead to them are very different. So essentially, there is a radiation which is put out. That radiation interacts with the stellar medium, and then there are other processes which basically happen. And that is why these different timescales are there in this particular problem. So this famous paper, which is called Multi-Messenger Observation of a Binary Neutron Star Merger, had about 3,500 authors, 950 institutes, 48 follow-up groups, 70 observatories, and as I mentioned, 100 instruments. So it was a big challenge keeping a secret for among 3,500 authors for about a few months. And as one of our colleagues basically mentioned, it was the most ambitious and emotionally charged campaign in history for any short-lived event. I always like to sort of compare it with what happened in the case of movies. So if the first discovery was like the advance of a talkies in the silent movie era, the binary neutron star event was like the advent of IMAX. You could see it in many different bandwidths. Now I will go very quickly through this. As you know, once you have the event, the parameters can be calculated, and therefore all the parameters can be inferred by doing the Bayesian analysis. And as I explained to you, because this is a neutron star event, it will be tidally deformed, and therefore in the waveform we will look for signatures of this tidal deformation. And indeed we could put a limit. You can't exactly say how much was the tidal deformation, but some limits on the tidal deformation could be put from this particular observation. So what are the firsts from this particular event? As we said, it is the first observation of gravitational waves from a neutron star system. So remember, when the binary pulsar was discovered, from that one event we conjectured that when it coalesces there should be gravitational waves, and we made a prediction of what the gravitational wave should be very accurately, and we confirmed that after many years. But remember, the first discovery was not from a neutron star system. It was from a black hole system, because a black hole system is more massive and therefore puts out a stronger signal. But we could not go to the funding agencies and put a proposal for looking for gravitational waves from binary black holes, because nobody had seen a binary black hole up till now. So you can see here that you have to conjecture something, but you have to base your proposals based on what the evidence is, and the evidence was only for a neutron star system. It was the first observation of a gravitational wave from an electromagnetic wave from the same source. And it supposed, many years back, people had said that gamma ray bursts could be created by the coalescence of neutron stars. So this supported the hypothesis that this was produced by the merger of two neutron stars in this particular galaxy, which created a short gamma ray burst. It was accompanied by what we call as a kilonova, which is a phenomena which happens because of the fact that when neutron stars coalesce, there is something called R process which happens, and nuclei are formed. There is a radioactive nuclei of those specific nuclei, and that basically leads to this phenomena which is called kilonova. So you can see here, Madhusudan emphasized told you about the spectroscopy which really happened. So you can see here that what we are really doing is not optical spectroscopy, but spectroscopy of nuclei. Nuclear spectroscopy is being done. You can really look at the chemical elements which are basically formed, look at the emission which comes out from these particular nuclei, and say something about how these objects are made in the universe. It's very surprising. We are so used to taking things like gold, silver, platinum for granted, but you would be surprised that up till today nobody really knew how these elements are really formed in the universe. Because remember, if you know your basic nuclear physics, elements up to iron are stable. So if you want to make things above them, you really need to have some other kind of processes. And people had believed that maybe violent events like supernova can create such heavy elements. But then if you look at the rates of these nuclear, the supernova, and look at the details, it turns out that it's not very easy to explain the abundance of these heavy elements. So now, for the first time, we have events like neutron star mergers, and in this particular case, one can show that you can really make a very large amount of silver, gold, platinum from such events. And it's very interesting that this particular event, after this event happened, almost about 700 papers on this particular object really has been written. This was, almost a year back. And even today, for example, observations, interpretation, models of this particular object really continue. And therefore, it is also sort of stresses the importance of collaborations between the gravity wave people, electromagnetic people, and probably in the future, maybe neutrino people also would be joining in this particular game. Can we do only astrophysics or can we do something more? It's interesting that even from this first event, we could do cosmology. One of the important parameters in cosmology is what is called as the Hubble constant, which basically tells us what is the rate at which galaxies in a particular galaxy would basically move if it is at a certain distance. Now, as Madhusudan explained, because of the gravitational wave emission, you can estimate, for example, the distance to this particular source. Because you have made an electromagnetic observation, you can calculate the what you call as the redshift of this particular source. So putting together the distance from the gravity wave observations and the redshift from the electromagnetic observation, you can calculate the Hubble constant and hence do cosmology. This method is more powerful basically because it does not suffer from the standard difficulty which happens when you determine the Hubble constant, and that is the fact that you use what are called as distance ladders. Up to a certain distance, you use one set of standard candles. Beyond that distance, you use some other set of candles, and in the interface, you have to match things. So this is a more powerful method to calculate the Hubble constant, and this is really going to be important in the future. I had also told you in the beginning, in my primer, that you can test general theory of relativity because general theory of relativity predicts specific properties for the gravitational radiation. I told you that light and gravitational waves really came by within 1.7 seconds. That basically tells us that roughly the speed of light and the speed of gravitational waves are essentially similar. Remember that whenever you make such statements, these statements are always statements, quantitative statements. So you basically will say something like up to factors of 10 raised to 10, to a part in 10 raised to 13 or to a part in 10 raised to 15, the speed of light and the speed of gravitational waves are essentially similar. So now you will basically have to worry about such quantities. And then, there are many predictions of Einstein's theory of relativity. I don't want to go into details. For example, I mentioned to you that in Einstein's theory, there is no dipole radiation. So in the waveform, you will look whether there is any signature for dipole radiation. I told you a very complicated formula where the coefficients were predicted by calculations which came from general theory of relativity. So if you can match your waveform, you can try to put constraints on how accurate the predictions from Einstein's theory match with the waveform and so on and so on. And as I told you that there are two states of polarization in Einstein's general theory of relativity, but if you have a more general theory of gravity, there can be 6 polarization states. So eventually, if you can determine the polarization states of gravitational waves, again, that is another way in which you can try to verify Einstein's theory of relativity. This is the things which happened from the binary neutron star. From the binary black holes also, you can do similar kind of tests, and I will not really go into the details, but I hope you understand the spirit that you have very, very accurate observations, so you can try to look at how much those observations are consistent with the theoretical prediction. So what you really need to do is create from alternate theories of gravity predictions of that particular theory for gravitational wave observations, and then check whether Einstein's theory matches better with the gravity, with the observations, or this alternative theory is. So this can all be done very conveniently by Bayesian methods of model selection and so on and so on. And this is essentially how the subject really is developing. So what have we really discovered? So what is shown here on this particular graph is the universe which we saw by using electromagnetic observations. By using electromagnetic observations, pulsar observations, you can see the electromagnetic neutron stars, and by some X-ray observations, you can also see electromagnetic black holes. As you can see here, all the masses are below 20 solar masses, and the masses of the neutron stars are clustered below 2 solar masses. The moment we went through the first two observations of gravitational waves, the first O1 and O2, immediately we found out there was a neutron star which was seen by LIGO and Virgo. It led to an object which was more massive. And if you look at the black holes which it created, all those black holes were more massive than the electromagnetic black holes. So we have discovered a new family of black holes which was not accessible to us by electromagnetic observations and probably would never be. So that is the whole power of a new astronomy. It reveals things which was not possible at all by previous methods. When people use the name LIGO, it was an acronym for Laser Interferometer Gravitational Wave Observatory. There was a lot of cynicism that people used observatory even before gravitational waves were discovered, and the gravity wave community had to face a lot of cynicism from the regular astronomy community because their argument was, you have not even detected gravitational waves and you are claiming that you will do astronomy with this. So you are not claiming you are a gravity wave detector, you are claiming that you are a gravitational wave observatory. It really is a kind of salute to the visionaries who led this particular field, because as you can see, even at its first discovery, the O has been earned so much that whatever was discovered was never possible by electromagnetic observation. So in a sense, the first discoveries have been transformative, and even in this first catalog of gravitational wave events which we put out, it discovered 10 binary black holes and 1 binary neutron stars. When we made the data public, a group which was not part of our group, the Institute for Advanced Study, the Princeton group, they used some slightly different methods, and they could also discover 8 more binary black holes in our data. So you can see here that a new game has basically started. We start looking for catalogs of binary black holes, and when we open up to the other people, if they use different methods, they can find out, more from our observations. So what is the current status of this particular subject? After the second run, the detectors, as I told you, were made more sensitive, and we were going to plan to run the detectors for not 9 months, for almost a year. What is shown here is that the improvement in sensitivity of each of these detectors, and usually it is sort of quantified by telling how far you can see if you had a binary neutron star, how further you can see. If you can see further, it means your detector is more sensitive. So you can see here that each of these detectors is being made more sensitive by improving its instrumentation and so on. And we came up with also something which was more challenging. We said that from now on we will not keep secret what we are seeing. The moment we think we see a gravitational wave signal, we will make a public alert and tell people that maybe there is a gravitational wave signal. If you want, you look for the optical or the gamma ray counterpart of that particular event. So we were in what we call an era of open public alerts. So the first the first half run began on 1st April and went on till 30th September. The second half was supposed to go till April 30th, but because of the pandemic, the laboratories were closed on March 27th. The Kagra detector was supposed to join us by the end of 2019, but because of some technical complications, they could not do that. What happened during this third observational run was that we sent out 80 alerts. That means probability that there is maybe a gravitational wave event. Remember, we cannot be very sure. Some signal can be basically because of the system noise. So after we send the alert, we look more carefully in the instrument and 24 of them were basically retracted because we knew that the disturbance was due to some instrumental reason. So you should be very clear that each candidate may not qualify eventually as a detection in the final catalog, because when we do offline analysis, we are more rigorous, and therefore from the alerts we will come to candidates, but finally those candidates will not be element in the catalog. And as I said, there is this, if you really are curious, just Google words like GraceDB, GCN circulars, gravity wave open sign source, etc. And you will see how we release these public alerts and what kind of information is released to the astronomers when we suspect there is something there. And indeed, because our instruments were more sensitive, suddenly you can see that in the O3 run, we really started seeing more and more events. Remember, these are candidates, and we are doing our analysis of the first half currently, and then we'll do the second half. So what is really required when you want to send a public alert? You can see what is really involved. You have to do what is called as send out low latency alerts. The moment you have you think you have a detection, you have to automatically vet it, try to classify it, very rapidly try to localize it, and this has to be done within a minute. And then you send out an alert to your astronomy friends. Then you work hard on it, you improve your parameter estimation. Humans try to see whether there is some instrumentation problem, etc. You improve the classification, and at the end of an hour or so, a little more than an hour or a few hours, you either send out an initial alert or you retract that particular signal. So you can see here a lot of time-bound activity is really involved, and the full community is sort of really involved. Somebody has to be on alert every 24 hours. On a smartphone, he would get a thing and then immediately he has to go on duty. And then, as I said, the classification is sort of improved. Depending on the mass of the system, it may take a few days or sometimes even more. And then you make an update. So you can see here that there's a lot of activity involved if you really want to send alerts and collaborate with your astronomy friends. But this was in place and very successfully worked during this particular object. When we have the data, the full data is analyzed to make a catalog, but we also come up with what are called as exceptional events. What we think are events which of a kind which you have not seen before. So what I'll tell you now are what are the exceptional events which we saw in the first half of the observational run. So I'll just tell you, for example, this event was seen by 2 detectors, not the third one. It was identified as a binary neutron star event. But when we looked at the total mass of this particular system, it was heavier than the neutron star masses we are used to before. So it was heavier than the neutron star which has been observed till now. That is why we call it as an exceptional event. Nobody, up to the electromagnetic observations has given us masses up to 2 solar masses, not much above that. We know where the distance is. When you try to localize it, it's over a larger region in the sky. It is further away. So even though it's a neutron star event, we have not been able to look for an electromagnetic counterpart. So whenever you see an event, focus on the distance and the sky localization and on the masses, and that is what you will see. Why that I call this why the collaboration called this an exceptional event and put out a special paper for this one particular event. Up till now, all the masses which we saw were roughly binary black holes of similar equal masses. The next event was a binary black hole which was seen by all the 3 detectors, but its masses was asymmetric. It was an asymmetric binary where the masses were in the ratio of 1:3. And the moment you have an asymmetric binary, something interesting happens in the physics. When you have a system of equal masses, you see its dominant mode, because the higher modes depend on the difference of the masses. So if the masses are equal, then the higher modes are in a sense suppressed. On the other hand, if the masses are unequal, the higher harmonics can be basically seen. And once you have higher harmonics, there is more detail of the waveform which is being seen. So you can make a better measurement of the distance and of the inclination and so on. What is seen in the graph below is the fact that the higher harmonic is very large, and you can see the second bump which you see immediately after it is the higher harmonic. So you can see here the higher harmonic has a smaller signal to noise ratio, but it is distinctly seen in the analysis which we basically do. Again, when we try to look for electromagnetic normally, for binary black holes, we don't expect electromagnetic counterpart, but we never know, maybe there is some new physics which we are missing. So even from binary black holes, we look for electromagnetic counterparts. Our astronomy colleagues look for electromagnetic counterparts, even though, we don't expect it to be there. So this was the second interesting event. The third one was even more interesting because it was seen by the three detectors. It was asymmetric, but the mass ratio was even larger. And then you can see the black hole was of the order of about 25 solar masses, but the smaller object was something which was less than 3 solar masses. And therefore, obviously, you will see that the higher harmonics can be even better seen here. The distance is given here, about 200 megaparsecs. But the sky localization was very good for this particular object. And therefore, we could try to do cosmology using this particular object because you could localize it much better. So we call this a dark siren. It allows you to determine Hubble's constant even without an electromagnetic counterpart. And the biggest mystery is the lighter object the heaviest neutron star, or could it be the lightest black hole? This is a mystery which is sort of waiting to be discovered. Now, what I want to show you is what is meant by saying that the higher harmonics. So therefore, I wanted to show you the great work which numerical relativity people can do to simulate these kind of objects. It takes a few months to get these particular waveforms, and that is what you will see in this particular simulation. The different colors are the different multipoles, and what you are seeing here is that as the system goes around, you see the dominant quadrupole radiation, then you have the octupole radiation, then you have the next multipole, hexadecapolar, and the different multipoles are put out at different stages in the spiral. Just to remind you that this is not, if you have learnt your electromagnetism, when you have a general electromagnetic field, you can break it up in terms of its multipole moments, and the higher multipoles come at higher values. So you can see here what you're doing here is you're taking the gravitational waves emitted by this particular system and breaking it up into its multipoles. And what is told to you is that when the system is asymmetric, there is a bigger chance to see the multipoles, and Einstein's equations give you this very, very precise prediction which of this particular waveform which really comes out for this particular system. Amazing work of our numerical relativity colleagues, and you can match this with the observation which you basically see. The last exceptional object was another big surprise, an object which was seen again by the three detectors. It was a binary black hole, but it was seen for a very short time, only for 100 milliseconds and only about 4 cycles at about 60 hertz. And when you looked at the black hole masses, there were about 85 solar masses and 66 solar masses. and the remnant was about 142 solar masses. This object is very, very far. It's about at least 2 gigaparsecs away, and no electromagnetic counterpart was really seen up till now. Now, why was this exceptional? Because when you look at black holes, up till now people believe that there are two kinds of black holes. Black holes form from stars, which are called stellar mass black holes, which are probably up to a few, tens of solar masses. And then there are supermassive black holes at the centers of galaxies, which are a few million solar masses. But then in between, there are objects which are supposed to be intermediate mass black holes. Also, theoretically, people believed that between some 70 and 120 solar masses, because of some pair instability, black hole masses cannot exist. So suddenly we have found an object in that gap, which we call pulsational pair instability mass gap. So we have discovered something. Either the theoretical prediction is incorrect, or this object is something different. It's formed from some different mechanism. And for the first time, we have been able to discover a new kind of black hole, an intermediate mass black hole, which was conjectured to exist, but there was no concrete evidence for such objects. So with the third catalog, you can see that we have 39 new gravity wave events, and the black hole events are more massive, and you can see them sitting in the top half, including this intermediate mass black hole which I told you about. Once you have a population of black holes, we start asking astrophysical questions. The kind of questions you ask is, what are the typical black holes like? How many of them are there? Has the population of black holes changed as the universe evolved? Remember, the universe evolves as you go backwards. So is the black hole population formation rate the same at all epochs in the universe, or does it depend on which epoch in the universe you are looking at? What about the formation of black holes using the gravitational waves which come out of them? So as I told you, they raise new questions about the underlying population, and it challenges the best theories of binary black hole population which we have today. There are different scenarios for black hole formulation, what we call field formation, dynamical formulation, or primordial black hole formulation. Which of them is really right, or whether all three are possible? These kind of questions we basically will ask. And then the important point is, as you can see, even with the third catalog, we are seeing a big spread in the mass, and we are seeing questions being raised which we could not really anticipate really would be there. And work like this essentially is what the collaboration does. And if you really will look at the archives, you will find that there is a preprint discussing these kind of questions by the collaboration. I just want to sort of emphasize, I have been talking about 2 Nobel Prizes. As you know, that the Nobel Prize this year was for Penrose, Genzel, and Getz. And this was for the theoretical foundation for black holes and for the supermassive compact object at the galactic center. Genzel and Getz, because they really could show that in the galaxy, in the center of a galaxy, there is a supermassive compact object. But the fact that the LIGO observations is showing up more and more black holes definitely was one of the reasons that the Nobel Committee, which is normally very, very, conservative, went ahead and really awarded the Nobel Prize to Penrose, who well deserved this Nobel Prize. So in a sense, I would say this really nudged the Nobel Prize to the for this year's Nobel Prize, because now, before the LIGO observations began, black holes were supposed to be exotic. Now, the moment you discover a binary black hole, we will say, oh no, you know. So we have become really taking the binary black holes for granted. We really think that they are an important constituent of the universe. I have now almost come to my end of my time, but I should not, I'll just go rapidly through this. So what will happen now is our detectors will really be improved. They are improved in a staged manner, and when you do that, their sensitivities will gradually increase, and finally we will reach the design sensitivity. In the next observing run, we basically hope to see more binary black holes, about 8 of them, binary black holes about 68, binary neutron stars about 8, and we have not seen a neutron star black hole system. We expect to see a couple of them. Maybe you will hear about them in the next few months, or maybe when we start doing our 4th observational run. And the other thing is the Kagra detector now has joined the network. So with the Virgo LIGO network, few hundreds of degrees was the typical size of the observation area. Because we have the Kagra detector, which is in Japan, the sky area will become on an average smaller, and therefore it will be even more sort of exciting. So we will have an extended detector network, and the network will include, as I told you, LIGO India. And when they come online, LIGO India will be like the best US detector, so it will be able to see up to 330 megaparsec when it comes online. So you can see here, compared to the Kagra detector and the other detectors, the Virgo detector, the LIGO detectors have a larger reach, and our aim is to be like the LIGO detectors. So if we come online in 2026, we will be among the best detectors on the earth, because we would be the newest detector also. Does our story end with the advanced LIGO network? No, because as you must have realized, planning these detectors essentially takes about 10 to 20 years to sort of realize. So if we want to go beyond the detectors which exist today, we really must be thinking about them even now, and the community is already doing that. After the advanced detectors, we will go to what is called as the A plus detectors, the Voyager, the Einstein telescope in Europe, the Cosmic Explorer, which is about 40 kilometers long detectors, and there is a space detector which is being planned, which is called as the LISA detectors. These third generation detectors essentially will drive all kinds of science. They will try to explore gravity in its extreme, matter in its extreme, and also, as I told you, be able to do cosmology. So they will also be able to say something about the cosmic history. When you look at optical astronomy, we don't look at optical astronomy by itself. We have electromagnetic astronomy, because you have radio astronomy, gamma ray, X-ray, ultraviolet, and so on and so on. So it's essentially 2 decades in frequency which you basically span. And when you look at the gravitational wave spectrum, you will find that even though today you are looking at gravitational waves whose periods are in a few milliseconds, the LISA detectors will look at gravitational waves whose periods will be of the order of minutes to hours. The timing arrays look for gravitational waves whose periods are of the year of years, and eventually maybe a dedicated mission like the Big Bang observer, which will look for gravitational waves from the Big Bang itself. So the point is that there are 2 decades in frequency to be explored by gravitational waves. So this is the just not only the tip of the iceberg, tip of the iceberg, because there's so much to be discovered. And once you have gravitational waves in different bands, you can do multi-band gravitational wave astronomy. You can try to see a source in LISA first, and LISA will predict that some source after 5 years will appear in the LIGO band, and therefore you look for it in the LIGO band. such kind of astronomy which you can imagine can really happen. And therefore, with these detectors, there is a big spectrum of gravitational waves which we will try to do. And once again, just remember the point which Madhusudan mentioned, that we are doing spectra of very large sources, very, very big astrophysical sources, but they are putting out a spectrum which we can characterize and use to identify their nature. So in a sense, we begin from known knowns, extend to known unknowns, but ultimately, of course, the excitement is in trying to find out the unknown unknowns by using gravitational waves. So I have tested your patience too much, so let me just conclude. Gravitational wave astronomy was ushered in with the first discovery of 15814, the binary black hole, and multi-messenger with the binary neutron star. And what was the game changer? It was the network of LIGO and Virgo and their ability to localize a gravitational wave source to a small enough region and send alerts to realistically facilitate electromagnetic follow-up. And as I explained to you, Kagra has already joined the network, and in a few years, LIGO India will join this network. The third observational run has consolidated the insights into astrophysics, cosmology, and fundamental physics. These were assessed as feasible, but it is amazing that it has remarkably emerged even at its first discovery. Normally, you conjecture something, and it is many, many years later that you realize what you have conjectured. Here, even at its first discovery, whatever we had sort of conjectured has really been realized. That is the power of gravitational wave astronomy. So in a sense, the first faint strains of the gravity wave whispers are really the whispers of a new astronomy. And as I explained to you, because we are able to test the general theory of relativity, new interfaces of general relativity and things like quantum field theory are already emerging. And obviously, Einstein should be very happy with that. So to all the young people in the audience, I would just say, please come and decipher the astronomy using gravitational wave astronomy, gravitational wave observations, and multi-messenger astronomy. Each of these blobs which I am showing you here is a discovery waiting to be made, and a discovery which should have impact on all the astrophysics and cosmology which can really happen. So with that, I end my particular talk with this particular slide, which basically tells us the richness which we are really observing. Thank you for your attention, and sorry for overshooting my time.
Thank you very much, sir. I may.
Sir, can we take a few questions?
Sure.
So first we'll have questions from the audience.
Okay.
So if any of you have a question, please come here. You can introduce yourself, your name, and then.
Hello, my name is Umar.
Who's firing? Do you need to change mute my video, audio?
Hello, my name is Umar, and I had a question about the two examples for gravitational waves.
No, it's not. I can't hear you at all.
Madhusudan, sir,
Ah.
you can communicate the questions to Professor.
Yeah, that may be better. Yeah, can you just write?
Both the examples which you gave for binary black holes and binary protons, they're related with circular motion, which is accelerated motion at the same time. I'm sorry. Wow. These two motions can generate gravitational waves as well, but when you talk about collision, when two galaxies collide or merge to form one, they also form gravitational waves. So does that have anything related with acceleration and velocity?
Yes, so the simplest thing to keep in mind is that gravitational waves are produced when the system, the quadrupole moment of the system really changes. So there has to be a quadrupole moment at the leading order and a change in the quadrupole moment, second time derivative of the quadrupole moment. So as you any time where there is acceleration, for example, as you're saying, when two things collide, there would be gravitational waves because the system would be sort of accelerated. So the reason we focus on things moving in our prototype sources are these binary black holes and binary neutron stars because their frequencies lie in the sensitivity bandwidth of our detectors. So I keep, in our talks we keep focusing on them. But you are perfectly right that any time there is an acceleration, you would be able to generate gravitational waves. But if it is not, if it is very complicated, it's not very easy to predict what those radiation will look like. And since the wavelength, since the strength of the radiation is very small, if you don't know what the radiation looks like, detecting it is more difficult. That is the reason we don't really, talk about it, but they definitely exist.
Yes, thank you.
Yes, we can continue.
And I also had one more question. How do you get associated with LIGO? Can you hear me?
Yeah, now I can hear you.
Yeah, how do you get associated with LIGO?
How do you? I didn't get the keyword. What did you ask?
How do you get associated with LIGO?
Okay, so as I said, at this particular point, when you look at LIGO, it has a program, and there is a program, where it sort of every year decides that this is what it will do over the next year. So normally what happens is that there are groups which essentially promise to deliver part of the particular program, and then there is an assessment made whether that is part of the LIGO program, and then people are associated and given access to the data which they require. So what happens in India, for example, is that there are 14 institutions where activity related to gravitational wave data analysis and experiment really happen. And those are groups which are associated with the LIGO experiment, and through them you can participate. So this is formal participation. But one more thing is that a lot of open data is sort of made available after a mandated time, and then that the algorithms which people use to analyze the data is also publicly available. So there are people who work outside the collaboration by using the publicly released data and publicly released software or their own software and try to do analysis of the LIGO experiment. So both these models are possible.
Okay, thank you.
Sir, there is one online question.
Yes.
There is a question from one of the online viewer. His name is Sumant. I'll
Mhm.
read out the question.
Mhm.
Please explain why an object with heavy mass that curves space-time. I repeat, please
Mhm.
explain why an object with heavy mass which curves space-time.
Okay, so Yeah, I could hear Anand's question. Yeah. Yeah, this question one should keep in mind, as Madhusudan mentioned, that this is a language which we basically use. So remember, the key thing is the fact that Einstein's equations are the key. Einstein's equations basically use the language, is sort of embedded in a language which is the following. It basically says that what we know in the absence of gravity is that we know that special relativity is valid, and special relativity leads us to what we call as Minkowski spacetime. But we know that the moment gravity exists, this spacetime cannot be Minkowskian, basically because of the fact that the length and time intervals are affected by gravity. Now, to efficiently embed this information in the theory, Einstein used the language of a curved spacetime, because in our understanding of geometry, a curved spacetime can be, a curved surface can be imagined as locally being flat. So this picture Einstein wanted to use to formulate his field equations, and therefore what really happens is that we assume that in the absence of matter there is flat space-time. As matter is added in, depending on the amount of matter which you are adding in, the effect of gravity is sort of coded into this space-time, and therefore a heavier object will curve space-time more than a lighter object. It's a picture which is really not, it's a convenient picture to use, but it's not to, for me it has never been very important. The equations basically are the truth.
So if I think we don't have any other question, so it is. Let me take an opportunity to conclude with a vote of thanks, and it is more than a tradition to thank a great personality like Professor Bala, who is with us. So we thank Professor Bala Iyer firstly for accepting to be a part of this program, having a person who is leading a large group working on gravitational waves, and who himself talking about a gravitational waves on this day. It itself is a great thing. I also thank Professor Iyer for giving the wonderful talk with detailed information which only people like Professor Iyer can give. On behalf of Jawaharlal Nehru Planetarium and participants, I thank wholeheartedly for your presence, sir, and of course for your valuable talk. Thank you one and all for being the part of this program on this day, National Science Day. Thank you very much. Thank you, sir.
Thank you. Thank you all who participated in this particular event. I appreciate your time. Thank you very much, Anand.
Sir, I will conclude the meeting, sir. Yes.
Yeah, Masudna on the call still?